Manju, I think you can start.
Ankit.
Sir, one request to all. Only speakers will deliver lecture in Zoom, so others can please join through Exporium. Is a request to all.
You can. Good morning, everyone. You could visit cmti.exporium.com and log in through your email IDs. If you haven't created an account, then you can create an account and just type in your email IDs and you'll be ready to log in. And there you could enter directly into the conference hall. And from there, you will be able to look at the live streaming of the talks that are being given. Thank you so much.
So good morning and welcome back all. Now the technical sessions will be started. Will be on nano manufacturing. A keynote lecture will be delivered by Prakash Vinod sir on the topic Technology Developments by Nano Manufacturing Technology Center. So before to that, I would like to introduce about our faculty today. So is my screen is visible? Can all of you see?
Yes, yes.
Yeah, about today's faculty. Mr. Prakash Vinod sir is a mechanical engineer and presently heading technology development activities technology development activities on smart manufacturing, precision machine tools and aggregates at CMTI Bengaluru. He has undergone training at Fraunhofer Institute of Production Technology, Aachen, Germany in development of ultra precision machines, at Oklahoma State University, USA in intelligent machining, and has 31 years of experience in research, design and development of high precision machine tools and its aggregates, smart manufacturing special purpose machines, micro and nano fabrication and characterization systems, completed prototype development of about 25 new machines products, provided over 300 consultancy services to industries in machine tool testing, dynamic and thermal behavior, noise and vibration and condition monitoring of machines, and nanomaterial characterization. He has over 35 publications in international and national journals and conferences, filed 5 patents, has received FIE Foundation Awards in 2013 and 2019 as Principal Investigator for the Innovative Product Developments, Intelligent Ultra Precision Turning Machine and Ultra Precision Diamond Turning Machine. For further specific queries, you may please write to email ID prakashv@cmti.res.in. So I will be I'll be sending to you all through chat box. You may please note down. And now over to Prakash Vinod sir.
Thank you, Manjunath, for introducing me to the audience. I will be sharing my screen and we will start presentation in a few seconds, please. Can you all see my screen? Hello?
Yes sir, it is visible sir.
Okay, thank you so much. So, the topic of my talk is basically technology development works done by Nano Manufacturing Technology Center towards Atmanirbhar Bharat. So this particular session, actually, I will be giving initial talk and then followed by other talks by my colleagues, 5 colleagues. So they will be in specific technologies, they will be giving you more details. So what is NMTC? I think by this time, I think you may be aware, otherwise Nano Manufacturing Technology Center is one of the COE established by Government of India DIPP, Department of Industrial Policy and Promotion, and later DHI. Once CMTI came into DHI, so it was supported by DHI, Department of Industry. So this particular center, the main focus has been to establish state-of-art national facility for developing, nano manufacturing technology at our country, and also to develop and propagate nano manufacturing technologies, products, and processes in our country. So these are the twin objectives, apart from this skilling and reskilling in this area. So how come CMTI? So I think if you people who are not aware of CMTI, so we have over the many years since our inception, we have been developing many innovative and focused technologies during our journey. So we started with machine tool technology development and also the subsystems which are required to facilitate machine tool technologies. So that's the way we started. Then later in 90s, we expanded ourselves, and we, apart from machine tool technology, other advanced manufacturing technologies has been also looked into. So somewhere in 2008, there was a proposal from CMTI regarding to develop, create facility and develop this nano manufacturing technology in our country. So since 2008, almost from last 1 decade, we have been working in development and propagating of this nano manufacturing technology in our country. So if you see, that this is our center, which is a COE. So as I mentioned, it is funded by DHI and DIPP. So the entire project cost is around 152 crore, and which includes state-of-art building infrastructure. Because as you know that if we are working in nano domain, which is very small and in this thing, so the environmental issues are going to play a big role. So we need to have a very state-of-art building infrastructure supported by equally important clean room infrastructure. So this together only can help us to do any development work or any service-oriented work in nano manufacturing. So that this was part of that project. Also, as we need to create national facilities for state-of-art facilities for developing nano manufacturing. So we had procured a lot of equipments which are required for micro nano fabrication and characterization. And later, as the project progressed, we also developed some of the equipments which are required for micro nano fabrication and characterization, and they were also added. So that is the thing. As we started developing technologies also, and we started adding to our facilities. So we have many product and process development labs in the center, and if you see, we have almost 16 nanotechnology labs, and each lab is there is separate environmental control for that. So we in some of the labs we are maintaining temperature down to plus minus 0.1 degree centigrade. And this ground vibration and all, floor vibration, we are maintaining below 100 nanometers level. And we have clean room labs with different classes, depending upon the requirements, class 100, class 1000, and class 10,000. So these are there. So, and apart from development of technologies, these are national facilities, and we are providing R&D support to industry and academia also in this nano manufacturing. And also on a continuous basis, we are doing skill development and technology disseminations we are doing. At present, NMTC has well grown, and at this moment we are collaborating with industries and academia, and we are developing many new technologies, which is inclusive of inclusive of machines, processes, many devices, and we are providing innovative industrial solutions. Innovative solution to industrial requirements. So, and some cases, different modes we are working with industries. So if you see, so we have already developed many technologies which are ready for technology transfer. To be precise, more than 25 plus products and processes we have developed, and some of them we have already done technology transfer, and some of them we are pursuing technology transfers. So there's a way we want to promote micro and nano innovation for transformational growth. So as you know that this nano manufacturing and nanotechnology are applied in many industries. So they are basically catalyst in different type of industries. So that we are trying to promote that and see that these different industrial sector, apart from capital goods sector, they are getting benefited out of this technology. So if you see, many products has been developed, machines and processes, and also that national facilities, it is available. We are providing services to industries in different things. So these are the, I think you can see, these are the machines and all which we have developed, and some processes. So processes for micro lens array, processes for microneedle, processes for diamond turning and all. So that plenty of processes also has been developed by CMTI. So this is our building. If you see that how it looks. So the building has a ground floor laboratory, as well as it has got underground labs which are 10 meters below, and and they are structurally disconnected, so that any activities happening at ground floor will not get transmitted that to underground. Environmental disturbances will not happen. And we are different labs. We are maintaining different temperature. Each lab is separately controlled, and also this is the way we are doing. So majority of our labs are in underground. Around 9 is around underground, and around 7 is in ground floor. So this is the way we are doing. So coming to the, before I go for the technology, what we have developed, and showcase you some of the things. I just wanted to, what are things we have done. So we have, some of the equipments we have procured, and for which is for micro machining and nano fabrication. So we have around 10 high technology tools which are meant for nano fabrication work, and around 15 high-end tools for nano characterizations, and around 13 tools for testing and purposes. So these are the tools we have, which is housed in our laboratory. These are the major tools. Apart from that, there are minor tools. And totally, we have 50 plus tools which are available at our facility. So the building infrastructure, as I mentioned, it is one of the largest underground facility in the world. I think in the varying country. I think though. So there we are having around 25,000 square feet of clean rooms where we are maintaining temperature and vibration to be very precise. The levels are, temperature controls are in plus minus 1 degree. You may not get anywhere, I think, in our country. Also, the floor vibration level also below 100 nanometer. Again, it is state of art technologies and all. So this is the way we have been working. Civil infrastructure also, according to that, it was state of art, and to take care of these environmental issues and all, and HVAC and all systems which are used for clean room and all, that's also state of art. So that's the way we have done. And this our facility is housing 50 plus tools costing around 65%. This thing. So we have been doing a lot of this product and technology development. So around 25 major technologies we have developed, and which are already ready for technology transfer and all. And further we are pursuing this and continuing further. So we have filed patents and publications, patent 6 numbers, other IPR 4, publication 60 plus and all. And we have been keep on focusing on skill development in this area. We have already trained 500 plus technical personals in hands-on, basically hands-on training, practical training, and also awareness in around more than 2,000 people we have done in this. We have conducted national conferences and workshops and all to disseminate this technology to the country. And we have been also targeting, that further technology development from this center, as our secretary was mentioning. So we have some vision to develop some few more new technology for industrial specific requirements in this thing. And our services, if you see, we have been already providing, we have already, this center has a customer database of around 250 customers from industries and major academias and all. And more than 4,000 individual tasks we have done, provided and successfully completed. Basically, these all tasks are basically R&D support to industries as well as to academia and all. So that we have been doing, and now our services are further growing, and we are targeting that more than 2,000 tasks will be doing every year. So that's the way we are looking, apart from the future technology development works from this center. So now I will take you to the some of the products and processes which has been developed at NMTC. So, and what are challenges we have faced, and how this technology we have made it in such a way that it is industry ready, from the point of view of because most of the technology what we have developed, it is it has to be globally competitive, means price wise and and from accuracy point of view, both point of view. So we have to look into both. It is, we are not question of development of technology. We have also seen that these technologies are affordable as compared to imported technologies. So that is the way. Then only our industry will adopt this. So that's the way these are some challenges which we have looked into that, and we have developed successfully. And I'm demonstrating some of the technologies, some of the success stories we are sharing with you. So one of the thing is that ultra precision turning machine development in our country. So if you think this is one of the technology gap which has been identified earlier. So in our country. So what is the ultra precision turning? Actually, it involves generation of ultra fine surfaces. Basically, the surface, if you look into surface quality, the surface finish in few nanometers are a value. Where in grinding, you are getting around at best 200 nanometers. But in these processes, we are expecting the surface finish in order of 1 to 2 nanometers. That is the way we are looking into that. So this is the called ultra precision turning, which involves, of course, either monocrystalline diamond tools or CBN tools. And it is done basically on vibration-free, chatter-free machines, which has exceptional accuracies, both in terms of spindle rotation and slide movement. So there's a lot of technologies going to build the machine. So for building the machines, we have to have a lot of technology, and so that those technologies have been developed by CMTI. Then only we can make it cost effective. So if you can see how we have done. So we have made how we proceeded. So we developed basically a first step prototype for that we call IUPTM. So there we have done twin purpose, where there we have developed some technology for diamond turning or ultra precision turning, also development of subsystem and all. And also we have looked into that, nowadays people are talking of industry 4.0 and smart manufacturing and all. So we have also seen that this is equally also in this also, it is a test bed for us for development and integration of various modules, which facilitates, which makes it smart and facilitates smart manufacturing. So that's the way we are looking into that. Then later, it is basically this machine IUPTM, Intelligent Ultra Precision Turning Machine. So we are keeping this as a test bed, and and we are keep on developing and integrating, testing, validating technology. And parallelly, we have looked into from industry point of view, what industry needs. We may develop many technologies, but it can be there in laboratories only. So what industry needs is that machine which is cost effective, versatile. Also, it can produce you accurate component at lower cost. So that is the way. So we looked into that, and we came out with another series of machines, like this we call Nano Shape T250. This machine can do. Earlier, this generally DTMs can do only, if you look into basic DTMs, it can do, non-ferrous, machining. It can produce very fine surfaces on non-ferrous materials, and so to some extent, maybe, some, plastics as well as some IR and all. But people are looking for machines which can do even hard turning, means which can, it can do, ferrous, hardened ferrous material turning also. So we have developed a machines which in the series which can do both. So this machine is much more versatile, and industry can adopt it. So that's the way we looked into that. So when we are doing this all development, so you can see the process development also plays a role. It's like a new technology when you bring, like a new method of, a new way of turning, that like diamond turning and all the technologies and all. Then process development also plays a role. So how to different type of materials like aluminum, germanium, silicon, steel, hardened steel alloy, and different type of processes for different applications like lens arrays, space mirrors, and all. So a lot of the process has been developed, and now you can see these machines can give in aluminum 6061, which is the optical grade. It can give you surface finish less than 2 nanometers RA value. In germanium and all, less than 1 nanometers, and in steel and all, less than 15 nanometer RA value. This is the way we have been developing this technology. So if you see, I was talking about that IUPTM. That was the first DTM, which we have developed under NMTC project. So in that, what we have, our focus has been also that to see that we develop many other technologies also, which are going to help us in long run. So that way, so we have not only we developed mechanical subsystems and all for that DTM, also we looked into the modules which makes machine more productive and user friendly, and it can do self diagnostics and all, and more accurate. So in this machine, we have introduced some new technologies like machine error compensation. Machines will have generally geometrical thermoelastic error compensation and all. So in real time, we have developed modules which are based on ML and machine learning and artificial intelligence, and can map the errors and correct it. Likewise, we also looked into machine diagnostics and all, self-diagnostics, and all such things we looked into. And also we looked into taking the information, through cloud and all. And process also we looked into. Machining processes also we can predict. So that also some modules we have developed. So this is the way technology development has happened in this. So you can see this machine. I just show you some, how we achieve the errors and all using AI and ML techniques. So like you can see, this is some geometrical error which is showing like linear error of one axis. The blue one is the raw error, and that corrections after corrections using AI and ML based modules, this is the red one is the value. So almost you can see we have brought down the errors in terms of nanometers level, whether it is a geometrical, linear error, or whether it is angular error like pitch, yaw, and roll, or whether it is straightness error. So all have been brought down to nanometers level using this in these machines using AI element techniques. Likewise, thermal error. I think we all are aware of this thermoelastic, deformations in machine tools and creating, a sort of, accuracy problems, job accuracy problems. So in this machine, again using AI ML techniques, we develop some modules, and the errors which are in terms of 50 plus 50 micron, entire shift I'm talking, not for the small time, which includes everything. So that we brought down to 3 micrometer band. So from 50 micrometer band, we brought down the errors to 3 micrometer band. This is the way we have been working. And I can just show you, I think, to go back and, sorry. Yeah. So this, this also after that, the development of these modules, we implemented in our machine, and then we validated. So like thermal, the thermal compensation techniques we adopted, and we started producing the jobs which has got, a radius tolerance of 1 micrometer only. So earlier it was going out. After machining 5-6 jobs, it was going out of the range. And after implementation of this, our thermal error compensation modules, we are able to control that error. So this is the way we have done that. So, so this is our state-of-art machine which we have done technology transfer. It's called Nano Safety to 250. So which it is benchmarked to the world best machine from both accuracy point of view and cost point of view. It is much more cheaper than imported machines. So definitely, then only we are able to do technology transfer to the industry. So otherwise, it could have been very challenging. So I will just show you one small video that about this, how we do that. So you can see this is a machine where we are, machining aluminum, mirror. We are trying to get aluminum mirror, and this is a work holding sector where the job is held, and this is the monocrystalline contour. So you can see, so small fine chips started turning, and you can see that you can get like a mirror sort of things you can get, on this machine. Why we can get? Because machine is almost, vibration and all we have control, and the accuracies of the spindle and the slides are in nanometers. Okay, so so now question is that, so I was mentioning that if we are developing ultra precision machine tools, if we start importing the subsystems and trying to integrate and do that, then it will not be cost effective. Even if you make technically, from benchmarking from technical specification, you can benchmark with the world best, but the cost wise also we'll have to see that it is quite lower than, and affordable. So all the subsystems of the machine has been developed. So this one of them is the ultra precision, hydrostatic slide. So you all know what is hydrostatic slide. So it is basically, it has got, high pressurized IL is used as a bearing, in between bearing elements and all. And this is basically, this is driven by linear motor, and it has, if you see the stiffness and all, it has very high stiffness. So it has stiffness in order of 1000 Newton per micron. So that way you can see almost 100 kg per micron is the stiffness. And with this, and in this also many technologies we have used. It has got, if you see that how we are getting the stiffness and all, it has got special sort of flow restrictors and all, which is allowing, if there is any load occurring on that, any displacement occurs, it will compensate it. So there is active compensation of the stiffness and all. So that is the reason we are able to get very high stiffness. This machine, and we have seen that we have developed many technologies and all, and we are seeing that the geometrical accuracies of these machines are very fine. You can see the straightness what we get in that travel is a 0.2 micrometer in horizontal direction and 0.4 micrometer in vertical directions. And this is a linear motor driven slide, and it has got very high precision glass scale as a feedback system. And together, if you are seeing, we are able to get positioning and all in this. Once we integrate with the machine control and all, we are able to get positioning errors in terms of nanometers only. So this is the way we are doing. So definitely, this slide we have used in our own machine. Plus, this slide itself, this technology is available to build other type of other machines, which can be used in case of high precision boring machines or jig grinding machines, jig boring machines sort of thing, or very high precision milling machines, and we can use. These slides can be used there also. Likewise, spindle. If you see the imported spindles, used for ultra precision machines and all are very costly. So if we start importing spindles and building the machine, the cost will not be able to compete with global prices. So what we have done, we have taken a challenge, and initially the first machine what we developed, there we have used imported spindle, but later that our nano shape machines, which we have, now we are targeting the industries and all. There we have developed our own spindle. So and there also that if you see the spindle, it is very aerostatic spindle, but it has motion errors. It's basically running errors in terms of nanometers only, and it has got moderately high stiffness also, very high damping, and it has, of course, we have used we have seen there is a laminar flow only occurring in the bearing. So there is no air hammer sort of effect and all. That is the reason we are able to get the errors, motion error below 100 nanometers. So this spindle we have developed for our ultra precision turning machine, but it can be also used for ultra precision hard turning. It can be used for ultra precision milling and micro milling. It can be used for ultra precision grinding machine, and the bearing technology can be used for building high precision measuring machines like form testers and all. So the way we are targeting. So later. We have done that also. We have built air bearing based rotary stage, which can be ideally suited for measuring machines like form testers and all. So if you see, it has the speeds and are lower up to 100 rpm, but accuracies are very fine. So accuracies are in terms of less than 50 nanometers. So that's the way we have done that. So this becomes another product. So which can we use it? Whatever technology development we do. So that can be used for multiple, applications and all. Likewise, that was one this thing regarding that ultra precision turning and the technologies, subsystems development, and how it is useful for machine tool industry. Now, there are other area we have worked on nano finishing by random finishing processes like abrasive flow finishing machines and processes. So there also we have developed machines, process technologies, and also even now we are working on the media development. So if you see what is abrasive flow finishing, it is a metal finishing processes that involves extruding of abrasive filled with semi-solid media, viscoelastic polymer media, and it is allowed to pass through the workpiece. So if this is a workpiece and this is the viscoelastic media and these are abrasive particles, they are they are forced or they are passed, they are made to pass through the job from to and fro many times. So that way it is finishing. It is removing some small quantity of material and it is finishing that. So this entire concept is there in books and all, but and some lab model was built at IIT Kanpur. So from there onwards, we have collaborated with IIT Kanpur and we built up a machine which is basically having all the controls and all, as well as features, which makes it more versatile. So it is basically PLC based, having HMI also. There process and all you can control and all, you can change the processes, you can there many features are there. So the way we are working and that, and then this machine we have done a lot of process development. many components from industries, be it is biomedicals like cobalt chromium prosthesis hip joint, or maybe from aerospace and from defense propellers, impellers, many things. I think almost maybe around 30 plus components we approve on these machines. So that is the way these machines are there. So if you see the technology behind that is definitely a machine which is developed by CMTI with the initial help from IIT Kanpur, plus also the fixtures. The fixtures plays a big role. As you know, as the media has to pass through the component in proper way, through the so these all are done at CMTI. We have developed technologies and all to develop these fixtures, and the media also plays a role. So media we have been working. Initially we used imported media, and now we are working on the media development so that we are self-sufficient, in that all aspects. So another technology is again it is basically for finishing. It is magnetic abrasive finishing technology. So this, if you see again, there also we worked with IIT Kanpur and initially. And if you see, the concept is very simple. In this super finishing technology, what we are doing is that we are creating a magnetic, sort of like magnetic abrasive media based brush. So that brush it is used, and if you provide proper movement to the job against the brush, then you can finish the component. So it looks very simple, but to realize practically and to see that it is useful, it has a lot of challenges. So we came out how to make it more useful, because if we try to make a magnetic abrasive flow finishing machine itself, it will have limited use. So we have what we have done. We developed attachment which can be put on a milling machine. Means this is attachment which is based on electromagnet based magnetic effect and all, and this can be put on the table of any milling machines, 3-axis milling machines, and there we have created that cavity and all, where we can form a magnetic brush like this, and then we can rotate the component and move the component in this cavity, so against the magnetic brush. So with that we have and this is very low cost attachment, so people can afford. So any machine tool manufacturer can afford to have this, and it makes it more versatile. So with this we have done. Apart from that, this media itself we have developed at CMTI. So if you look into the magnetic abrasive media, which is consisting of it can have different abrasive particle like diamond, silicon carbide, or quartz based, along with iron, this thing, so which are mixed and sintered and then put in form of abrasive media now, so that in powder form. So that also development was CMTI was done, and we could characterize, because we have scanning electron microscopes, and also you can see the image. So how these are the how it is that how abrasive these things are, abrasives like silicon carbide and all, they are on iron base, how they are sticking to that, how adhesion and how they are working. The adhesion has to be good, otherwise it will not be able to finish the when it is an operation. If adhesion between the base iron particle over that this abrasive, if not good, then it may not work. So that lot of work has been done even to develop this process technology. So next one, it is there on additive, micro additive manufacturing system. So CMTI I think has used a technology called MSL, which is again it is available. These technologies are already there in, on book, on techniques are available, but the realization of machine to do that has been done by CMTI. So in MSL, what happens that we can fabricate 3D component by curing layer by layer of a photopolymerizable resin. So what we need is that photopolymerized resin, and we need a UV light, and then we can cure layer by layer. So these concepts are there, but to realize, to make a 3D component, we have to do a lot of things. So then what we did to prove the concept and all, we have put a setup for MSL, microstereolithography on optical table, and we realized the concept and it works very fine. There also we worked with Indian Institute of Science and all, so we could realize. Later, we need to develop machines which goes to industry. So what industry looks, they don't look into the concept, they need a productive machines, where the productivity rate of 3D printing is very high. So then we came out with a projection microstereolithography based micro additive manufacturing. There we are using digital mirror display systems, and which they are, instead of building line by line, or the slow process of building the 3D component layer by layer, we can in one shot we can do that. So that is a technique what we have developed, and then this becomes a productive machine. and which can be, which industry can use and make cost-effective components. So we have proven again the process development plays a big role, and we have proven the process on the microneedle scaffolds for tissue growth and all. Various types of MEMS component, biomedical components, stents, and all many things we have done. So this is a machine which we are marketing for industries and all. So that if you, it is actually what happens that it takes of course the digital image from the 3D component, and then step by step it slices, and the step by step at different steps it has its own the CAD images that goes to a digital the digital micro display systems, and based on that this works as like a virtual mask. So based on that feature at that layer, what are things needs to be done according to the mirrors are turned on and off, and then UV light falls on this DMD and directed to the component and polymer regime, and then the it is cured, and then again it is moved up to cure another layer. So that is the way we are building. So this requires a machine, machine mechanism. Also that we have created HMI software and all, where the process parameters can be controlled. So it is not easy. Different materials requires different process parameters. So that way, so we have to have a versatile machines which can do all. So with this, we could realize many components, and which industry it can realize also many components. That's the way we are looking into that. So another area where we have been working in the development of nano characterization and fabrication systems. So nano manufacturing uses many nano fabrication system and characterization system which are imported. Even CMTI also we imported initially many of the things, but they are very costly, and technology development needs to be done in our country for that also. So then what we did, we started, we have taken a small step. What we realized is that most of the nano characterization and fabrication system use some sort of 3D scanner, which is having XYZ movements in terms of micrometers and with the resolutions of nanometers and all. So we have developed nano positioning system, which is 3-axis positioning systems with certain specifications and with resolutions of less than a nanometer. And then we started working on developing of the equipment based on these technologies and all. So this is heart of most of the nano fabrication equipments and characterization equipments, where the scanning is done, where that there is scanning movements and all. So then later we have developed, we worked with some industry partner, and then together we developed with a system which is we call it compact portable scanning tunneling microscope. So it is basically scanning microscope and scanning tunneling microscope, and which is using that wonderful that forces and all between tip and the job, and so that is the way we're working. And we built an entire system, very low cost system again. So this cost almost 1/5 or 1/10 of the imported cost and all. So that way we have we came out with these things which can this STMs and all it can come this thing. So as there is a gap between the probe in STM, scanning probe and all, and it is a family of scanning probe microscope. So as the gap between tip and the substrate comes down, so there is a tunneling of electrons and all happening between this thing. So that can be used to in terms of a gap between this, and it can do the surface profiling, and also it can do a lot of other things like it can find out some electrical characteristic of the samples, and so this can do many things. And this we have come out as a product, and to bring down the cost also. See, these systems, they require very quiet environment. So we have developed the vibration isolation, acoustic isolation systems and all, which are all patented technology by CMTI itself. So with this, all this, we are able to offer the product at very low cost. So that is the way we have entered into this area. So another, that when we were doing ultra precision machine development, we realized that okay, we are developing some of the spindles and all, where the accuracies are in terms of nanometers, running accuracies. But how do we evaluate that? So if you look, when we looked into, we found that these tools are available with some few people in abroad, which are restricted, sometimes for even exporting to India also, and it also the feature wise also they restrict when it is supplied to India. So then we thought that how we can go ahead with this development of spindles without this our own having our own spindle error measurement system. So we developed spindle error scope, which is basically spindle error measurement and analysis systems, and which can measure the spindle running accuracy of spindle in as per ASME and ISO standard, and which is tab based. So that way. So with this, our own software algorithm and all we have developed, and which is tab based, and some hardware probes and all we have to still import, because this capacitance probes and are not available in our country of that accuracy. So that we have to look into in future. But by doing this all, we could that monopoly of people we have broken, and we can provide solutions. And this is again we have the technology. If you see the package, this package is almost 1/3 of cost of imported system. So with this, we are able to map the error of spindle, as also we are able to find out the reason why the spindle errors are more. What is the reasons and all? We are able to investigate into the errors, and and we are able to help OEMs and all for corrections. Another module, when we are doing ultra precision machine development and all, we realize that we see that most of the ultra precision machines are that they require some sort of balancing. When there is a fixtures, different type of fixtures mounted on the spindle and all, they need a dynamic balancing. So in situ only. So now the present practice is that you have an offline system. You take it as and when there is a requirement of, you feel that it needs to be balanced, you take it, spend time, stop your work and do that. So we developed a module which is basically a software based, also has hardware like sensor and data system, which can be integrated. It's like an add-on module, and it can correct the unbalance. It can even measure the unbalance. It can be integrated with a control system to show you what is the vibration level as well as unbalance level when you are doing the work. And also it helps you, it's a user friendly, and it helps you to do single and double plane balancing on the machine itself. Yourself you can do it. So this is another module. This product is we have done, which is we are it's ready for technology transfer. Some few more products. I think you know that in our group and all, some people worked on development of Microneedle. Okay, so then we developed Microneedle, the process technology we developed, and then afterwards to apply, where to apply. So then we have realized that this Microneedle patches can be used for EEG measurements. Like now EEG measurement we are doing wet electrodes and all. So if microneedles, what is microneedle? Basically, these are small needle shape, conical shape. The tip is around maybe 5 micrometer, which can pierce to skin, and the total height will be around 100-150 micrometer. So that way, and this if you create array of this microneedle and make as a patch, then it can also it can take the biopotential. And if it is coated properly, and proper coating has to be done, then it can capture the biopotential from the body. So it can be used for EEG measurement, or it can also be used for sleep and alertness monitoring from brain and all. So a lot of things can be done. So we did benchmarking for EEG measurements, and we saw that the performance is equally good. So this technology also that we are offering, which is Microneedle, we call electrode. We can create electrodes, and with using our technology, industry can create electrodes and can supply for different measurements, maybe for biomedical applications and all. Another group of our this thing, they're working on surface engineering, and focus basically on thin film coating. So under that NMTC, we had procured some thin film coating equipment. Then the thing is that with that we have brought down many industrial solutions. That's called process development. So we have developed processes for surgical equipments, knives, sort of things. And then processes for watch casing and all. So that is basically DLC coating, diamond like carbon coating. So with using DLC coating of different configuration, because different applications are like for watch, what we are looking is the wear resistance and the look. Whereas in knives and all, we require some sort of some slightly toughness to be more. It should also be wear resistant and like that. And DLC coating for guideways, DLC coating for night vision lenses. There the requirements are different. The DLC coatings are used for like a filter to take that IR spectrum in particular range. So various type of application is just by DLC coating. Our team, our people have done that. So they're there. Likewise CNT. So we have grown CNT, and then based on CNT, various process applications have been, which is useful for industry, has been done. like super black coating, that CNT based UV that sensor, and also that CNT plus metal, sort of like thermal interface materials and all had been developed at our center. We have in this our center NMTC, we have created facility for micro machining using laser. So in that we have two type of lasers which are used for micro machining. One is femtosecond, which is using of burst of very short pulses, femto in order of femtosecond for ablation of materials, and other one is excimer laser, which is actually is also using very small and precise spot at very low wavelength. So that using these two tools, variety of applications have been process and application has been proven for by biomedical applications like microfluidic channels for blood samplings, then drug delivery systems, then sensors for like micro heaters and all, micro heaters elements, then cantilevers and all for scanning probe microscopes and all, then different flexure components for different applications, masks and all. A variety of applications have been done by our team, which are all industry ready and where the technology transfer is possible. So likewise, we have a tool for focus and beam milling, which which is basically the focus and beam milling uses a liquid metal ion source like gallium and removes materials in the basically nanometers. It removes. So if you see, this is the silicon. If you see on my screen, this is silicon wafer, and there the entire CMTI logo has been created, and the length of this logo is around 10 micrometer, and this height is 2 micrometer, and depth is nanometers in the few hundreds of nanometers only. So this is possible on the silicon wafer, and this imaging also done using our scanning electron microscope. So this tool, this is just a technology demonstrator, but we are using this tool for finishing of very diamond tools and all for getting control waviness. Also, this can be used in semiconductor for failure analysis, for circuit editing and all. So there's various of applications we have created which are very useful for industry. So these are all the products what I want to tell you. And I like to mention that we have not done everything alone. We have been associated with many organizations which are both in India and overseas, like IITs, IIT Kanpur, IIT Madras, and Institute of Science. And abroad, we have been working with University of Michigan, Oklahoma State University, and Western Michigan University. And we have many technical collaborators like BARC, NAL, I2N Technology, and all. So we all together, some few of the products, they also have worked with us. So now, just in a few minutes, I will close. We have all these now facilities are there for which is helping us to create new technologies, and we are looking forward for developing new technology for nano manufacturing. But we have plenty of facilities which are available for people to use. So if you see fabrication facility in the NMTC, we have around iron beam milling, we have ball mill, we have diamond turning machine developed by us only, abrasive flow finishing developed by us, projection MSL developed by us, femtosecond laser, excimer laser, PCVD, PVD. These are all tools. We are developing technology, and also we are helping other industries. They can come forward with a problem. We can develop technology with them, or they can take services from us also. If they don't want to work with us, they can take services from us. Same wise, we have plenty of characterization tools. 15 I have listed. One of the best facility in our country for characterization at nano level. So it includes variety of equipments which is for microscopy, whether it is optical microscopy or scanning probe microscopy or electron microscopy using SEM-TM. We have one of the high resolution TM with CMTI. We have mechanical property characterization. We have nano indentor. We have micro hardness tester for optical characterization. We have spectroscopies, interferometries, and all systems. We have for crystallinity and texture study. We have XRDs. We have for particle size and all. We have particle size analyzer, surface area analyzer. We have a full-fledged electron microscopy sample preparation tools. So where we have around 15, 16 tools which are used for preparation of samples and all. So these all facilities are available for industries and academia. And these are some of the customers we have. I told you that we have, in this thing, we have around 300 plus customers. And some of the customers, they are regularly using our facilities. So I just listed them. So there are other people also important to us. It's not that, but just few people. So from different domain, from government R&D labs, from private organizations, from PSUs, from academia. We are serving everybody. So thank you so much, and this is the end of my presentation. If you have any questions and all, you can. We are ready to take it forward. Thank you so much.
Thank you very much, sir. The participants, one request is that only the questions which will be received in Exporium platform under Q&A will be answered. For any specific queries, you can always write to us, and the queries will be answered through mail or through any mode of conversation. So only questions will be answered which will be received in the Exporium platform under Q&A. So as of now, there is no questions in a Q&A platform.
Okay. No problem. You can go ahead. We are ready. I think mail ID is also here shared in beginning, and also it is available. Must be available in the
I have already shared your email ID also, sir, through chat box.
So,
I'll be sharing.
We are there to help people, and also we are getting ready for the phase 2 of our development activities, and we are ready to collaborate with industry also. So that is I wanted to end my presentation. Thank you so much.
Thank you very much, sir. Now our next session will be on single point diamond turning, SPDT, and the lecture will be delivered by Mr. Gopi Krishna. So before starting the session, I would like to introduce our faculty. So this is about our faculty. Mr. Gopi Krishna is a scientist at CMTI, Bengaluru. He has specialized in the field of ultra precision engineering and systems development for past 12 years and has expertise in advanced manufacturing and indigenous product developmental activities in ultra precision engineering domain. He has completed prototype development of about 5 new ultra precision machines products, TRL 7 to 8 levels, which are indigenous developments of the country. He has published around 8 publications in international and national journals and conferences. He has received FIE Foundation Awards in 2013 and 2019 for developmental contribution in CMTI's innovative product developments, Intelligent Ultra Precision Turning Machine and Ultra Precision Diamond Turning Machine. Recipient of CMTI's Best Scientist Award in the year 2019. He has guided MTech and PG Diploma project students for CMTI's research activities and have coordinated CMTI's training programs on single point diamond turning and micro and nano fabrication courses for industrial participants and researchers. So if possible, you can note down the email ID. As I earlier informed, I'll be dropping his email ID through the chat box. It is gopi@cmti.res.in. So over to Mr. Gopi Krishna. So we can take over. Thank you.
Thank you, Majina. Just start sharing my screen. Manju, whether my screen is visible?
Yeah, your screen is visible.
Yeah, it is in full screen.
Yeah.
Good morning to everyone. Today I'm going to talk about single point diamond turning. It is basically an overview of the diamond turning process. Okay, single point diamond turning is nothing but a turning process where we use a monocrystalline diamond tool to machine in a high precision lathe. It is also called an ultra precision diamond turning machine. Here we will be able to get a surface finish down to nanometers and a form accuracy down to submicrons level. So this is basically done on a very high precision machine, so that there will not be any vibration or any geometrical and thermomechanical errors which gets reflected on the component. So you can see the component. You can able to see the mirror finish on the component. The surface finish is in the order of 5 nanometers or less. Okay. So why diamond turning? So basically, for non-ferrous materials like copper, aluminum, and all soft materials, the other process of lapping and grinding becomes a very tedious process, and you will not be able to get a very good surface finish and form. So diamond turning provides a very feasible and prominent process for attaining surface finish in the order of nanometers, and form tolerance down to 1 micron. And okay. So which all materials can be diamond turned? Basically all the non-ferrous metals like aluminum, copper, brass, gold, zinc, tin, silver, all this non-ferrous metals, and the polymers, coming to polymers like acrylic, polycarbonate, polystyrene, PMMA, all this also can be machined. And apart from that, we can also machine IR crystal materials like germanium, zinc cyanide, zinc sulfide, and silicon. So all this non-ferrous metals can be easily diamond turned. There is a limitation of physics. We cannot use a diamond tool for machining ferrous materials because it leads to diffusion wear and excessive wear of the tool. So that is why steel materials cannot be machined by diamond tool. But however, there are new technologies which can be adapted to even machine steel materials, ferrous materials using diamond tools. So in this presentation, I'll be talking about those processes also. To have a overview about diamond turning, this is a Taniguchi curve which has been proposed by Dr. Taniguchi long back. So this graph shows how the accuracies of the machines keeps improving as the years gets advanced. So in this also, the single point diamond turning process has been shown as the ultra precision diamond turning machines, and which is accuracies down to nanometers. So single point diamond turning plays a major role in advanced machining processes. Though many people, we may be using all the components which has been done by diamond turning process, but we may not be aware. Few may not be aware of the process as such. So I'll just touch upon the basics of diamond turning over 1 or 2 slides. So basically, in a normal turning process, when we try to cut a material, we'll be cutting along the grain boundaries. Because the tool edge radius will be in the order of few microns, basically in the order of 50 to 100 micrometers. So we may not be able to cut within the grain boundaries. So we'll be cutting the work material along the grain boundaries as shown here. So what happens is the surface finish and the form accuracy will be limited to the grain structure of the parent material. So, but in terms of diamond turning, the diamond tool, what we use is a monocrystalline diamond tool. So we can sharpen the tool down to nanometric radius. So here the edge radius of the tool will be in the order of 30 to 50 nanometers. So because of that, we can able to cut within the grain, so that we can able to get ultra fine smooth surfaces like mirror finish. So that is the main reason how we are able to get a nanometric surface finish, even with the bigger grain structures on the component. So and also because of the sharp radius, we can able to give a very fine cuts also. If we have a normal turning tool, you should have a maintain a minimum 100 micron depth of cut and or more. But in diamond turning, you can go depth of cut down to 1 micron or less also. Okay, this is the physics behind the single point metal cutting mechanism. So to give an overview for the comparison for conventional and ultra precision machine, see the cutting forces in a normal lathe will be in the order of 1 to 100 Newton range force, but in diamond turning process, single point diamond turning process, you will be in the order of very few milligrams, like 0.01 Newton to 1 Newton, or maximum 2-3 Newtons. So the chip cross section also, and again, as I was telling, the depth of cut what we can give here are down to 0.5 micron to maximum 30 micron, or you can go a little higher also. But in normal turning, you cannot give lesser than 0.1 micron, 0.1 mm depth of cut. Automatically this leads to a lower chip cross section area and also to a lower cutting forces. Okay, and accuracy aspects. When we compare in a normal lathe, you can get a dimensional accuracy down to 10 micron and profile accuracy down to 10 micron on components. But in diamond turning process, you can get it down to 0.1 micron or 0.5 micron profile accuracies. And surface finish in the order of 0.4 micron best what you can get on a normal lathe. But in ultra precision diamond turning, you can get down to 2 nanometers or even better in certain materials, and maximum up to 50 nanometers surface finish. So here the tool plays a major role here. Basically, what we use is a monocrystalline diamond tool. It is not a polycrystalline diamond. So the entire diamond is a single crystal. So because of that, we can able to have a very sharp edge radius along the edge, so which makes the cutting very smooth and very easy to cut the materials. So here again, like any other tools, the tool also here also you can have a positive zero rake angle and a negative rake angle tools, and you can have a controlled waviness along the nose radius, because that defines what accuracy you can get on the component. And also you have a cylindrical clearance and a conical clearance angles based on the finish cut or the rough machining processes. As I was telling you, the edge radius is less than 15 nanometers or finer than that. Okay. So again, the tool are classified into multiple this classifications. Like the tool can be a monocrystalline natural diamond tool, or it can be a synthetic diamond tool based on the requirement of the user. And the profile again can be of cylindrical or conical clearance. The waviness can be controlled or non-controlled. And you want to finish a very high accuracy components, you may have to go for a controlled waviness tool. And the top rake angle or zero rake angle and negative rake angle also is there for machining ductile material, brittle materials. And the tool shanks also plays a major role here. Coming to tool shanks, you have multiple tool shank options. So basically, people go for steel for a lower cost option, and people also go for tungsten and carbide tool shanks for having a very high overhang machining applications, where it gives a very good stiffness tool shanks. And molybdenum they used to use for dampening high frequency vibration, which may affect the surface quality. So molybdenum basically harass the vibration coming from the other sources to the machining area. And also people also use titanium also for very dynamic response applications, like fast tool servo applications, which I'll be talking later. So apart from this tool, the work holding also plays a major role. The chuck mechanism in a normal lathe, you have a 3-jar or 4-jar chuck mechanism, but in these applications, you cannot directly use a 3-jar or 4-jar chuck because it may distort the component during machining. So in order to support the component without stress-free, what we do is we have a different chucking mechanism in this machining process. And apart from that, it should be very easy to operate. And also the component, whenever we mount rotationally non-symmetric component, the spindle rotation has to be balanced also. So the chucking mechanism should have a balancing provision also in such a diamond turning process. So I also was telling there are multiple work holding mechanism, and here we use a vacuum checking process. So you see, this is a spindle on the diamond turning machine, and this is a vacuum chuck where it have radial grooves across the chuck. So once we keep the component and switch on the vacuum, the component gets folded to the vacuum chuck. So this way, it minimizes or almost eliminates the distortion happening due to the other chucking mechanisms, like 3-jar chuck or 4-jar chuck or clamping mechanisms. So this also gives a very good accuracy. So if such kind of vacuum checking fixturing is not available, what happens when we try to machine a spherical profile, and when we remove the component gets distorted in microns, which may not be affected in a normal lathe process. But in terms of ultra precision machining, it affects the component in micron level. So your accuracies will go poor on the component. So this check mechanism also is very important in these machines. And basically, there are multiple design criteria. If at all you want to have design your own work holding fixtures for this diamond turning process. Not only it limits to rotationally symmetric components, we can also machine non-rotationally symmetric components by designing a different types of fixturings for holding into the component. If suppose here you can see a off-axis segment where which needs to be machined So here, if you see, the profile is offset from the center of the axis. So in that mechanism, in this requirement, what we have to do, we have to mount the same off-axis segment offset to the center of the component in a specific custom designs picture. So that way we can able to machine the component as desired by the engineering requirement. So this picture also shows here where off-axis spheres are being machined. So you can see multiple off-axis mirrors are machined, which is mounted offset from the center of the spindle. So that way, the parent axis is maintained, and this offset from the center can be mounted as per the design requirement, and you can machine the components as such. So these are the fixturing advancements which can be done on a single point diamond turning process. We can now we'll just look into the component accuracies what we achieve using single point diamond turning process. So on different material, as I told you, it can machine on multiple materials like aluminum, copper, brass, and all that. Here, if you see, you can get a surface finish down to 1 nanometer and 2 nanometers in aluminum and brass and copper and all other materials. And here we can even machine silicon and germanium, which are crystalline materials, IR crystals. So basically, these materials, when you try to machine by other process, it tries to have a brittle fracture on the surface. But here we use a process called ductile rejoin machining, where we use a negative rake angle tool, which gives a very high compressive force on the surface of the machine component, like germanium, so that the surface doesn't subject to cracks. So this way we can able to machine again a mirror finish on the components like germanium and silicon. So as I was telling you, this can be machined with a very high compressive force using a negative rake angle, and also other parameters like critical depth of cut, and also the process feed parameters also plays a major role here. The critical thickness for different materials are very important to get a very good surface finish on this brittle materials. So we'll just have a look at the applications where this diamond turning is widely used. So coming to applications, as I was telling that brittle materials like germanium and silicon and other materials are widely used in defense application, IR thermography systems, and night vision applications. And coming to metal mirrors like aluminum and brass, all this are copper, are widely used in space applications like space mirrors for satellites and telescopes applications. And again, the ductile materials are again used for night vision and IR thermography applications, what I was talking about. And apart from that, medical industries also, the intraocular lenses which they do for cataract surgery for older patients. So the intraocular lenses are also fabricated using this process with a smaller single point diamond turning machines. And the contact lens molds are also manufactured using this process. And precision machined components also are done using the single point diamond turning process. And the automobile, the light reflectors, and also the photonics application, the LED molds. These are all day-to-day application components which we see around us. So these molds are basically manufactured using this single point diamond turning process, and they by injection molding, they make mass production out of these molds. As I was talking about the SPTT process, it is not only the process technology which is important here, the machine tool also plays a major role here. It is not just if you put a diamond tool on a normal lathe, you'll be able to get a surface finish in the order of a few nanometers. So the machine tool also plays a major role here. So as Prakash sir has earlier explained about the features of the machine. So this machine also has a aerostatic spindle system compared to a normal lathe where we use a ball bearing mechanism for bearing supports. Here we use air bearing support for the spindle, and we use hydrostatic slide mechanism for movement of the X and Z axis. So that way we used to get a very good motion accuracy of the slides and spindle. And again, it will be mounted on a granite bed because to have a very good thermal and vibration stability. And again, this granite bed will be supported on vibration isolation platform. So this gives a very good vibration isolation to the machining process, and also we'll be able to get a very good surface finish on the components. So this is the basics behind the machine construction of these machines, specialized machines. So as I was talking, there are multiple machine features which also plays a major role, which I will not touch much further because our previous speaker has addressed these things, like the structural stability of the machine, the fluid film bearings like hydrostatic and aerostatic spindles, the drive mechanism plays a major role. The feedback system also should be of a higher accuracy. The geometrical and positioning accuracy of the machine should be in the micrometer range. The machine should be able to isolate the vibration which is generated from the outside surface, and it should have a very high-end motion architecture controller. The system resolution should be down to 1 nanometer, and we also should have a distortion-free work clamping system, and we can also integrate error compensation modules to the machine, so that the error accuracies which comes out of thermal errors during this high pressure machining can also be eliminated in real time process. This nanoshape T250 machine, which we have developed at CMTI, and it has been spoken elaborately in the previous lecture. So this machine is what we have done at CMTI, and we can make all these diamond turning applications on this machine. And CMT has worked on 3 generation developments of this machine, and we are working for the past 25 to 30 years in this technology. And the latest launch is the NanoShape T250 machine. And also covering the basics of SPDT. Now I'll just touch upon the advanced diamond turning techniques, what is evolving in the recent years. So they basically like 3 classifications I've done, like fast tool servo diamond turning attachment, laser assisted diamond turning attachment, and ultrasonic assisted diamond turning attachment. So we'll just start with the fast tool servo. Basically, as I was talking about
Oh, looks like we lost his connection. We'll resume back.
hello. Hello. Yes, sir. I just joined back, sir. Yes, yes. Hello.
Yeah, shall I share the screen?
Yeah, you are able to see.
No, not yet.
I've just shared it.
Ah, okay, no problem.
Is it visible?
Yeah, yeah, it's visible now.
Okay. I'm sorry. There. I think there should be a intermission here. Okay. As I was talking about the micro lens fabrication. So here the fast tool servo mechanism we can able to machine non-reticulating centric components. You can see how good you can able to machine individual lenses on a micro lens mold, and you can also have a surface finish down to few nanometers, and also you can get a very good profile accuracy on these components. Not only limited to periodic lens designs, and also we can have multiple lens designs like honeycomb structures, and also like the compound eye mechanism. So these are all the latest advancements which is happening in photonics area, and these research can be easily materialized by using a single point diamond turning process to fabricate these kind of lenses and components. And the other advancement, what I was talking about, is the laser arrested diamond turning process, where laser light is passed through the diamond tool to machine the component. So here, what happens is the laser passes through the diamond tool and it locally softens the material. Basically, this is this laser arrested diamond turning is used for crystal materials like IR crystals, like germanium and silicon, where the tool wears are in larger rate. So what they do is use this laser diamond turning process, and it locally softens the material, and again we can able to machine the material like a ductile material. So this is a very cost-effective process to have a very good tool life on the component, and we get a very good surface finish on the component. So using this laser arrested diamond turning process, silicon can be machined down to a few nanometers, and also the silicon carbide, which is very tough material, can also be done using this laser arrested ductile lithium machining process. And one more advancement is the ultrasonic arrested diamond turning process. As I was telling, the steel materials cannot be machined using diamond tool. So what they do is they locally vibrate the tool in ultrasonic range, so that what happens is the tool vibrates in an elliptical form, and it will not be in continuous contact with respect to the steel material. So that way, the diffusion wear will not take place, as the two diamond will not be in continuous contact with respect to the steel material. So this way, we can machine the component, components also through ultrasonic assisted process. So this way, there are attachments are available in the market which can be bought and integrated to the diamond turning machines what we have. So the tool vibrates as per the sinusoidal wave. You can see there will be a very less period of contact it will be there, and it keeps engaging and disengaging the components. And again, the amplitudes will be in the order of 2 to 3 micron, and you can able to machine all steel materials using this process, using a diamond tool itself. So with this basics lecture, I like to conclude my lecture on single point diamond turning. If there is any questions or anything, you can just post it to my mail ID, which is being posted by Mr. Manju. Thank you.
Yeah, thank you very much, sir. Dear participants, kindly if you have any queries on this topic, please come back to us. Please write to us. And again, as there are no questions in Q&A platform in Exporium, so I think we conclude this lecture. So
Thank you, Manju.
yeah, thank you very much. So now our next session will be on the topic nano finishing, abrasive flow finishing, magnetic abrasive finishing, and deburring process. And this lecture will be delivered by our faculty, Mr. Naveen. So I would like to introduce our faculty. So is my screen is visible?
Yes, Manjunath, it's
Yeah,
visible.
yeah, thank you. So our faculty, Mr. Naveen K, is a scientist at Central Manufacturing Technology Institute, Bengaluru. He has completed his master's in Advanced Materials Technology from UVCE Bengaluru. He has over 8 years of experience in the field of precision products and process development for machine tool and micro rapid prototyping machine. He has published over 8 publications in international journals. So this is about our faculty, Mr. Naveen K. His email ID is naveen at cmti.res.in. You can write to him regarding any specific queries. I'll be sending you his email ID through chat box. So now over to Mr. Naveen K. Thank you.
Thanks, Manjunath. Naveen here. Can you hear
Yeah,
me?
yeah, I can hear you.
Okay. Can you see my presentation?
Yeah, I can see.
Okay, it's appearing full screen, right?
I think if you have, yeah, it's full screen.
Okay. Good afternoon, everyone. So I am Naveen. I'll be presenting on nano finishing processes, and also I will highlight some of the work that is been carried out at CMTA on this field. Abrasive finishing basically involves like particles with multi-point cutting tools. So this finishing actually is a last stage in the production. So before that, it actually basically follows process like milling and turning. So you can see uh, in the abrasives have been shown in the SEM image. Okay. And here you can see how the milling operation leaves. Just a minute. Can you hear me? I think I'm comfortable with
Now
not
slightly
using.
earlier your voice was little louder. It is dropped a bit. Your the loudness.
Okay. Yeah. Now it is fine.
I think it can be little louder. Initially it was fine.
Is it fine?
Okay, a little bit louder.
Okay.
Yeah, now it's clear.
So yeah, in this screen you can see like how initially the pre-machined surface texture will be after say a milling or turning operation. So generally this abrasive finishing, the abrasives are going to remove material at very small quantity. Okay, they are only going to remove the peaks according to the abrasive size that we are going to choose. Okay, and gradually we end up with a surface, a finished surface. Okay, how do we measure? Like we generally use, say, a tabletop and handheld profilers. So one must take care that we should measure perpendicular to the lay direction and not parallel to it. That is how we get the actual surface finish values, and some of the roughness parameters will be there commonly used like RA, RZ, RT. Like say RA is a arithmetic mean. So to indicate what is the surface finish on any given surface. So when we see a profile created, so it is going to have a form, a waviness, and a roughness all converged actually. So generally here there is a I have shown a machine tool with slides and a spindle actually. Okay, so when generally on the right corner I am showing a turning operation. So when there is if your tool is say blunt or something like that, so there is going to be a chatter. Okay, that we signature is, we can call it as a roughness. And that tool blunt tool is only one of the reason. There can be many other reasons. So, and if your slide is having a form error, so you are going to get a form as it has like this. And if your spindle has some run out issues or like that, then we tend to have a waviness. So generally in abrasive finishing, we can smoothen the surface by removing roughness and to some extent waviness. But form, it has to be done like in the prior process, like say grinding. Okay, when we talk about surface finish, yeah, different processes are there which are able to give different values of surface roughness. So in yellow, I have indicated like nano finishing process. Like a lapping can, we can achieve up to 20 nanometer, a owning say up to 50 nanometer. And there are some advanced finishing processes like abrasive flow finishing and magnetic abrasive finishing, which can, with which we can achieve up to 10 nanometer surface roughness. Are you able to hear properly? Hello?
Hello, yeah.
Okay. Okay. So a surface texture after misting processes looks like this. Uh, so this is how the turning and milling roughness, like say up about 12.5 micron RA. And with turning we can able to achieve up to like say zero point 0.8, even 0.4 is possible. It again depends on machine dynamics and your tool condition, how sharp it is. And when we can also see a grinding process where we can achieve up to say a zero point 0.4 to 0.3 micrometer. And with lapping we can achieve up to 50 nanometer or 20 nanometer in some of the cases. Okay, and how the texture of the you cannot see the lay direction after when it reaches less than 0.3 and 0.2 with bare eye. So why do we need this abrasive finishing process? Like sometimes there are different requirements. Sometimes in bearings and all we need friction to be reduced, and sometimes in wear has to be reduced, or a better appearance. Like say if you are doing plastic injection molding, you require a mold with very good mirror like finish. Okay, so that the component also end component looks similar way. And reflection like telescopes and space mirrors, and also in cutting tools. Okay, as to some of the tools are lapped. So when we talk about nano finishing process, you can see that in a product life cycle, in a manufacturing life cycle, there is a tendency that the finishing process can actually account for up to 75%, which is very significant. The reason being like you need skilled labor, you need very high end equipments. Okay, and consumables are also very expensive. So when a designer is specifying surface finish in his drawing, so he has to be judicious in like specifying what is what is, how much is sufficient. Unnecessary values if he specifies, then it results in product cost being on higher side and not being competitive. So some of the applications of nano finishing, say in automotive field, engine head, then in hydraulics, the direction control valves, then in rotary components, bearings, metal seals, gearbox, and healthcare like knee joints, hip joints. Then in metrology, slip kit. So you can see that there are diverse applications everywhere. Nano finishing is required. Name whichever field. So when it comes to principle, it is like one is energy bound, force bound, or track bound, and space bound. These are only four principles, one of by which any process will work. Okay, like say energy bound is abrasive machining, abrasive blast machining, or abrasive jet machining. Free abrasive machining like MAF, AFM falls under force bound. Track bound, it is like honing and all. Then space bound, it is like lapping. So that is how it goes. Then abrasive can be like from softer aluminum oxide to hardest diamond. Okay, these are the commonly used abrasives. And generally they are very small because you are only going to remove a very minute quantity of material precisely. That is why we need finer abrasives. So when we talk about abrasive size, it is mentioned in grid size. So like say it's in numbers like 60, 120, 220, 400, 800, that way. So the smaller the number, the coarser the abrasive is. So here you can see how the abrasive looks like. This is the coarser abrasive with a smaller grit number, and is the finest abrasive with a larger grit number. So, and this is how the table looks like when we go for procuring abrasives. So I will just briefly touch upon this process before going to some of the advanced processes which CMTI is involved in. So the lapping, it's like two surfaces are rubbed together with abrasive between them. So both mechanized and hand lapping techniques are there, and we have abrasives mixed with lapping media, and it is spread in between lap and a workpiece. So generally like a metrology artifact uh, like gauge blocks and all are generally lapped to, I believe, less than 20 nanometer. That is when you can ring it properly. So generally the perception is that lapping means we will do only for flat surface, but it is not like that. So a lapping can be for cylindrical surface, a spherical surface as shown here, but accordingly we will design the lap here. So yeah, this is a for spherical lapping, and here you can see the how it is being done, tooling and all. And this is for say cylindrical components, hollow or solid. Okay, and this is how the lap looks like for OD finishing. And a ID, it is a concentric tube which we can tighten it according to our what is to be achieved. We can slowly then loosen it or tighten it depending upon what we need. So at CMTI, spear lapping attachment has been developed, okay, which can be fixed to any lathe, or it can also work independently. So generally these spherical artifacts are used in metrology. One such application is even like CMM calibration. So, and even these spherical components have application in biomedical field like hip joints and all. So we have developed spear lapping attachment which can achieve less than zero point 0.5 micron sphericity. And quickly I will discuss about honing. Okay, it is again a multi-edge tool coated with continuous surface contact between tool and workpiece. That is how material is removed in honing. Okay, where the tool will be rotating as well as a longitudinal movement will be there. And this is how the tool looks like, a mandrel with honing sticks attached to it. Generally we use it for again bearings okay, and mainly for engine bores, it's a common application. Okay, what is specialty owning? It's like it tends to give a hatch pattern surface when you look into the bore of any engine. Okay, I see engine liner. So you will see that there is a hatch pattern inside. Okay, the main okay, based on the longitudinal oscillation speed and rotational speed, if you are able to control, this is the formula, okay, you are going to get different angles as desired. So when we are talking about engine cylinder liners, okay, we actually require bearing tribological property. Okay, we want the surface to retain oil into the surface, so that the motion is smooth and no seizure happens. Okay, so you have to plan initially. Initially, the peaks are removed using a smoother honing tool, and then later on, the metal that has become embedded in the cross hatch is removed with very fine smoothing tool. So, in a series by series, we remove the material so that we leave some of the serrations in that where oil can retain. If the same thing is done by lapping, which is also possible, it will you will end up with a very fine surface, and you may not have bearing tribological properties, and heating may happen. So these are some of the hydraulic components and some machine tool components where honing application is there. Now in real life, the components are not like cylindrical or flat. Okay, the components are much more complicated, like say knee joint, a hip joint. Okay, in biomedical area, or in automotive, like a manifolds, fuel injectors, various things, and in aeronautical components, impellers, uh, and some hydraulic components, manifolds, and also in so many machinery components. They are all not very easy to finish by this traditional lapping and honing techniques. That is when we need advanced finishing methodologies for precise and economical way for batch production, complex and intricate geometrical shapes, uh, and also to have uniform surface finish, to overcome labor intensive nature of traditional finishing operations discussed earlier, and for better process optimization whenever required, and nanometric surface finish requirement, and lower stresses in the job. These are all various requirements that arises. So CMT has developed abrasive flow finishing machine AFM 150D. Okay, we will discuss about this. The machine is capable of producing up to 100, working at up to 100 bar pressure, and also it has facilities like rotary work fixture, and also temperature control is possible to adjust the viscosity of the media. And the features of this machine is like you can do finishing and deburring of ID and OD of components, radiusing of sharp edges and inaccessible areas, rotary motion to improve performance, temperature control. So with abrasive media, how we do is like we generally we start from coarser. It is like it's a, like a polymer viscoelastic media. We mix it with abrasives at 1:1 ratio, and then initially we try to mix it with a coarser abrasives, and we like any other finishing process, then we try to remove the peaks, and then we go for finer and finer abrasives and try to achieve our desired surface finish. So basically the machine has two cylinders in between which the abrasive media mixed with abrasives polymer media. So it is made to reciprocate up and down in, and this simple cylindrical hollow tube fixture work component is shown here, within which the media tends to move up and down. So after various cycles the job is finished. So basically the media is a viscoelastic media. So the elastic components tends to have a radial force and viscous component tends to have the axial force. Okay, that is how the wall of the inner component tends to get finished in this. So we have a roll mixing machine, two roll mixing machine, with which we mix the media. Okay, whenever we have a component, a complex component, the challenge and the need is that we design fixture accordingly. Okay, how good the design of the fixture is, that is how we it should trace the profile of the job with good precision, good profile, so that whatever media it flows through the internal passage and finishing happens. Yellow is the job here. So here one more case where for one of the aeronautical component, engine component, okay, we have designed the fixture and it is actually bolted, okay, and the gray portion shows how the media flows through this fixture. Some of the applications are like hip joint, like aluminum propellers, femur, center tube, shuttle valve, or we have served for aerospace and also textile, then biomedical industry. Okay, it's all shuttle valve. Okay, it's for automotives and for aerospace and also for watch molds we have done. So the market potential of AFM, it generally it will overcome time-consuming processes. Then also the cost, finishing cost, in here it's significantly lower compared to other processes, and also we are able to do high precision components finishing in economical way. And so far there is no indigenous development of such machine. Only worldwide, only one or two are there at present who are making such machines, and they are in heavy demand. Technological solutions, aerospace, defense, medical, automotive. We are also serving for academics. We are providing finishing service. Next super finishing process, advanced finishing process, magnetic abrasive finishing. So it is again, uh, when we talk about a magnet, it's like there is a north and south pole and the lines are flowing between these poles, which we are aware. We actually make magnetic abrasives which are attracted to these lines, and then through relative motion between tool and the workpiece, uh, finishing happens actually. And the media is a special media which is like developed in combining magnetic particles along with abrasives, because as we know the abrasives are non-magnetic. So this is the tool that we have developed as an attachment for existing machines. Uh, uh, this we have developed for finishing cylindrical components like up to 10 mm, but this can be customized to any diameter for ID, OD, and for length. So primarily it is for cylindrical components. This electromagnet based component, and I am showing here permanent magnet based component. So both are possible to develop both type of tools. So, and we have also worked on flat finishing. Here you can see the flat component finished, and we have worked for 304 metal, aluminum, brass, and copper. This for some trial components, and internal components are also we can finish. So the finish value up to 20 nanometer is achievable. RA up to 20 nanometer is achievable on all these components. So you can see the media how it is attracted between north and south pole inside the cylindrical tube, and when we rotate the job, the finishing happens. We have developed abrasive media. Okay, so this is a magnetic abrasive media. Initially, we have sintered and broken into particles. So here we can see how the abrasives are projecting all across the media. And initially, we will have a rough surface with several peaks, and then this is a abrasive particle with abrasives along the outer surface. So after the cutting action, we achieve the smoother surface. So general applications are like primarily for cylindrical components, cylindrical tubes, pharmaceutical, nuclear applications, uh, and also IC engine valves, bearings. So you can see process variables, what are all are involved. Whenever we are talking about a free abrasive finishing process, there will be a lot of parameters to be optimized. It is like a simple fishbone diagram. This goes with any other advanced finishing processes. So now again we are having, I will just I'm finished with whatever areas what we have worked at CMTI. Now I'll give some short glimpse about what all real life components and how to finish them. Some 3D printed components generally are known to have very high roughness values because of particle size limitation. So generally, to start with, we have to have sandblasting, shot pinning, and drag polishing to reduce the surface roughness, and then we can go about with AFM or other finishing processes. So for cylindrical tubes, there is alternative like electro polishing process where we can again achieve very good surface finish. Again, but only drawback is uniformity is an issue in electro polishing. When it comes to optics, I think SPDT has been discussed already in previous lecture. The alternative with respect to abrasive finishing is that a fluid jet polishing techniques are available and bonnet polishing techniques are available, which are again able to provide a nanometric surface finish. Belt grinding is again a process where a coated abrasive belts are used. It is very versatile process. It can be used up to say 100 nanometer. We can have surface finish on flat and cylindrical components and other intricate shapes. Uh, Now, what about plastic components that we see in real life? So plastic components generally arrive from say molds, okay, which needs to be finished. And though there are so many nano finishing processes, advanced nano finishing mechanized processes existing, people still tend to do it by a manual laborious way using some of the tools, bristles and brush type tools, handheld tools, which has a scope to improve in future adopting these advanced techniques like AFM and all. So and plastics again, like a bead blasting method, we can finish it. And there are like drag polishing, which is again upcoming process, which has found a good usage for all this healthcare and automotive components, as you can see here. And it is the gears again. And generally polishing is one thing where actually material is not removed. It is unlike any other super finishing process. It just gives the luster on the surface. So because in polishing there is only rolling and sliding, that is the mechanism which is taking place, whereas in other finishing process the rolling, sliding and cutting, which is cutting is the major thing. So this only removes the only the top peaks and enables light to reflect and gives. So it is not a super finishing process, but again if for many applications it is good enough. Thank you.
Yeah, thank you very much. Dear participants, again, you can come back to us later regarding any questions on this session, or anything it may be on this topic. And as I can see, there are no questions in Q&A also. So thank you for delivering lecture. So
Thank you, Manjunath.
yeah, now moving. Actually, we we had a session on microstereolithography. Mr. Hari Krishna Tota is running on some network issues. He will reconnect us with us later. So now our next session will be on surface engineering. The lecture will be delivered by our faculty, Mr. Ankit K. So I would like to introduce our faculty. So Mr. Ankit K is a scientist at Center for Micro Nano Manufacturing and Metrology, Central Manufacturing Technology Institute, Bangalore. He has worked on various technologies like micro 3D additive manufacturing systems, focused ion beam and scanning electron microscopy, and thin film development for various applications. His current field of research is in the development of thin films for sensing, thermal interface, and corrosion resistance materials. He has developed CNTs and DLC for various mechanical and optical applications. He has authored over 23 publications in various journals and conferences, one book chapter, one patent filed, and developed several technologies for industrial assimilation. His email ID ankit at cmti.res.in. This is about our faculty, Mr. Ankit. So now over to you.
Thank you very much, Mr. Manjunath, for introducing me. Probably if you stop sharing the screen, I can.
Yeah, I have done.
So hope it comes. Please bear with me for a moment.
Yeah.
I hope my screen is visible now.
Yeah, it's visible.
Right. Okay. Good afternoon, everybody. Thank you for tuning into this virtual exhibition and virtual summit conducted under the aegis of Azadi Ka Amrit Mahotsav by CMTI. So today I would be talking about the surface engineering activities at CMTI. So to begin with, these are some of our activities. We work basically on diamond-like carbon nanotubes, and also we synthesize metallic thin films. In diamond-like carbon, we work on night vision applications, high hardness, hydrophobic, and low coefficient of friction. In carbon nanotubes, we prepare super black coatings, sensor heads, and now currently we are working on rapid cooling technologies, that is thermal interface materials. And metallic thin films, we do basically micro heaters, catalyst layer coating, and also for metrology applications. We have basically two equipment, a plasma enhanced chemical vapor deposition and a PVD. So we have our product called as Kavach DLC, which we have filed for a trademark already, and that is with respect to our diamond-like carbon coating. So today's contents are going to be, because we have only about half an hour, what I'm going to do is I'm going to introduce about the surface coating, surface engineering, a few applications of that, and talk about CVD, PVD, and what systems that we are having. Just introduction to CVD and PVD, and then I'm going to talk for a while about what are the coating activities that we undertake at CMT. So I understand, Manjunath, it's about 12:58, almost 1 p.m. correct?
Yes.
So
right. Yeah, it's exactly 1.
Hello.
Yeah. Is it?
Am I audible?
Yeah, you're audible.
Right. Because I thought I lost my network. Yeah, fine. So please let me know if I've, I just had a power cut over here. So let me see if in case it's not working, please give me a feedback whether I'm speaking or not, Manjana.
Yeah,
Is that okay?
Sure.
Yeah. So let me start with what is surface engineering. So surface engineering is a branch of science that deals with the modification of near surface structure, chemistry, or property of substrate in order to achieve superior performance or durability. So it's a kind of a technology, wherein you modify a surface either by doing etching, or you can even do coating. And it's basically about combining chemistry, physics, and engineering aspects with metallurgy and material science to bring about a certain property of a material. So then today what we are going to emphasize is on coatings, essentially. So what is basically a coating is, in simple terms, it's a layer of material or fluid that is applied to a surface of a substrate to impart a functional property such as wear resistance or corrosion resistance, or hydrophobic nature, etc. A coating can also be applied to impart aesthetic value to the product. So what is surface damage? When we talk about surface damage, it is something which related to, you keep a material in rain. So that's an environmental issue which happens. If you keep a block of iron in rain, what will happen to that? Due to humidity, or due to oxidation, or due to rain, icing, there will be change on the surface of the iron block. So it will start rusting, it will start corroding. You will see that, rust forms and small pieces of rust try coming out. This is because of, environmental issues. Let's say you bring it near a flame, then it has a different sort of surface damage. If you increase it to high temperature, then there is another sort of damage. So let's say you dip it in acid, or you dip it in an alkali, or you expose it to some salt. Then you have different kinds of damage. So probably it eats away or form a different sort of layer, or you find some sort of white formation on the surface. And then let's say about mechanical wear. So you put it under certain strenuous application, then it undergoes wear, abrasion, or friction due to the duress that it has to face. So let me talk about applications. Manjunath, I am still online, correct?
Yes, you are. There absolutely no problem.
Right. So the different applications that we have for thin films. So now I'm going to get into something more than the coating regime, and that is going to be thin films. And that is going to be the crux of the entire talk today. So let's think that there is a thin film coating. I'll come to what thin films are later, but I'm going to talk about the sort of properties, and you will be able to realize the importance of it. So let's say that you have a glass, a reading glass. So you see a kind of a blue tinge on the glass, which is basically for, anti-reflective sort of coating. And then there are certain costly glasses where you don't see that tinge. So that is UV cut or some sort of an anti-reflect or anti-glare coating, and these are all nanofilms. Multiple sandwich layer of somewhere about 100 nanometer, 50 nanometer coatings of different layers are designed. And then interference filters in some sort of measuring equipment. Then you have decoration coatings on various glass articles. Then let's talk about memory discs like CD, DVDs, and Blu-ray discs, and then coating in waveguides. And then looking at electrical, so you can do either insulation coating, you can do conduction coating used in semiconductor device. So today, any device that you have from morning to evening, maybe a cell phone, maybe a television, all are semiconductor devices, and they at least have 5 to 6 layers of coatings. Nano coatings is present, and that's an understatement. There are usually more than 100 and a few hundred layers, but just to on a safer side, I'm telling you that there is at least 5 layers of coatings if you consider your gyroscopes on your cell phones or accelerometers on the cell phones. Then coming to magnetic, that's your hard drive disks. So these hard drives also have coatings on that. Then chemical coatings, barriers to diffusion or alloying. Then protection against oxidation or corrosion, which is usually used. This chemical and this thermal coatings are basically used in aerospace coatings on the rotors of the gas turbine engines. And similarly, you have mechanical coatings for scratch resistance, improvement of hardness, some sort of micromechanical coatings, basically for tribological applications. So regime of coating, if I put it this way, then the regime of coating would be, it has a thermochemical diffusion, which is in terms of few angstroms. Ion implantation is also in terms of few angstroms to few nanometers. When we talk about physical vapor deposition, that would be a few nanometers to about a few microns in nature. Electrolysis and electroplating coatings are always 10 microns in the bow. CVD coatings go somewhere from few nanometers to about a few microns. And build-up welding is something when you are in ship and there is a sort of, due to corrosion, there is a hole. Then what people start doing is they use a welding torch, and then they try to bring the material around the hole and try to plug it in with by melting it and then doing covering it up, and that's called as build-up welding. And then, of course, thermal spraying, which is also widely used, which goes to a few hundreds of microns. So now let's talk about thin film coatings, or more colloquially called as the nano coatings. What are they? So nano coatings are coatings that are produced by usage of some components at nanoscale to obtain desired properties. So how do we categorize it? It can be categorized as multi-layer coatings, nanocrystalline coatings, with individual layer thicknesses ranging from a few nanometers. And then you can also create nanocomposites out of that, and I shall be showing it to you in further slides. And then you can play around with the grain size of these coatings in down to nanometer range, so that you can try playing around with the properties of the film. And of course, you can, a nanostructured crystalline material is one in which the spacing between lattice defects approaches into the atomic distance. So it's actually atomic layer thin coatings can also be possible, is what I'm trying to tell here. And these all sort of things, strongly influence the chemical and physical properties of the material. And nanostructured coatings offer great potential for various applications that I just spoke in the previous slide. In fact, even today, even your toothbrushes are having some sort of nano coatings. The bristles have some nano coatings so that you are able to remove the plaque very easily, and so on and so forth. So what are the essential differences that we are talking with respect to conventional coating or nano coating? So conventional coatings are usually micron to mm scale structures, whereas nano coatings are nanostructured materials and are in nanoscale thicknesses. So conventional coating have high contact tension between water droplet and, of course, the coating layer, and contact tension is much reduced, and you can have water repellence sort of phenomena here. Conventional coating, moisture can penetrate into housing. So let's say if you are still having an electroplating, and if you take a microscopic image, and what by means of microscopic image I'm talking about SEM image, you will still find that let's say you have done a chrome plating on steel, you will still find a 1.5 to 2 micrometer gap, which is not possible to see using naked eyes, and hence even moisture can penetrate through that small gap. Whereas nano coatings is basically addition, atomic addition, and hence it's absolutely a zero gap sort of phenomena. And that's why it's much better. You won't have any sort of moisture penetration there. Of course, surface roughness is typically based on the sort of coating that you achieve. And 5 micrometer, it's not 5 micrometer exactly. It depends on the sort of process, and it can range anywhere from few microns to even 25, 30 microns. And whereas on nano coatings, it basically conforms to the surface roughness of the part that you are having. So if you're having a silicon wafer which has about 3-4 nanometer surface roughness, then your coating conforms to that, and that is also about 3 to 4 nanometers surface roughness. So obviously, nano coatings gives you an improved benefit in this aspect. So now I shall be introducing to you with respect to two sort of techniques. One is a chemical vapor deposition, and the other would be a physical vapor deposition. So let me begin with the chemical vapor deposition technique. So a CVD is used in the deposition of non-metallic and metal organic films. Several optical coatings, super hard coatings, protection coatings, aesthetic coatings like gold color on watches. Not these days, but before they were using titanium chloride. Of course, today they use titanium nitride and they use PVD systems for that. So what are the pros and cons? Is that the pros are basically high coating hardness, good adhesion, good throwing power, whereas the negatives of the process would be, it's a high temperature process typically, and you could end up with certain amount of distortion. Sharp edge coating is slightly difficult because, let's say, if there's a burr in that region, thermal stresses are likely to develop and the peel off starts from that place. A limited range of materials can be coated, and of course, there is a sort of environmental concerns with respect to the release of process gases. So you have to put in a scrubber, then you have to take, that is of course not for all gases. Let's say if you're using a silicon-based gas like silane, then you will have to put in a scrubber and burn it out and then release it to the atmosphere. Whereas with respect to physical vapor deposition, here it's basically a physical target that you are having, and the physical target is etched out when you let in some sort of a gas inside, and this is physically transported from one place to another place, and then you are able to deposit metal, ceramics, and even like titanium nitride, aluminum oxide, titanium aluminum nitride, molybdenum disulfide, etc., etc. And you can start making composites using this. So PVD processes are now, which are widely used for making coating. So for example, there is a lot of companies which make gold coated god artifacts. So if you are having some god idols, they do a thin film pure gold coating on that of about few hundreds of nanometers to give that gold feel. Also, gold coatings are done on a lot of jewelry as well. And for example, there are certain costly watches where they coat with gold on straps and on the watch case. So on with respect to aluminum or titanium. So these are also done for various other applications. So talking about the pros and cons of this process would be, it has excellent process control, low deposition temperature, dense and adherent coatings. You can play around, you can have different alloys, different compound coatings are also possible. And PVD processes are typically vacuum processes, which come with a certain high capital cost. And then they have size limitations as well, and low coating rates. So based on the material and the target that you have to select a suitable coating duration for that, which is relatively low. And if you don't play around with power or the size of the chamber or other parameters, you typically have a poor throwing power, majorly owing to the density of the target that you are using. So the PED and PCVD at CMTA, we are having two equipment. The PCVD has RF and microwave, but essentially we use only RF here. We can coat acetylene and methane, and the others are basically for dilution. It goes up to 700 degrees centigrade, and a substrate of 8 inches is possible to be coated, and we offer this for surfaces. Similarly, PVD is used for, it has RF, pulse, DC, and DC. You can have metal and even ceramic targets as well. And it goes up to 600 degrees centigrade. It has about 3 into 3 inch targets and 1 6-inch target, which has a rotation of about 20 RPM. So, so far, so good, I believe. Manjunath, I guess everything is okay. So I'm going to start with the final set of the activities. Is that okay?
Yeah, before to that, I'll confirm you. I'll just check the backend whether we have any questions on this session or what.
Yeah, sure.
Let me refresh it.
Right. Maybe what I'll do is I'll just finish up with this section as well, and probably I can take the questions at the end, if that's okay.
Yeah.
Right?
Please, yeah.
Right. So the first thing that we do at CMTI is diamond-like carbon coating. So just to give you a brief introduction about what diamond-like carbon or DLC is, that it's an amorphous crystalline mix of carbon. So it contains both sp3 and sp2 content. Has a typical hardness value between 18 to 22 gigapascal. Offers very good scratch and wear resistance properties. And also it has a low coefficient of friction and hence acts as a good lubricant. So DLC can also be used for various applications for, scratch resistance, wear resistance, chemical corrosion in certain cases with respect to, salt or marine applications. It can also be used for optical applications for infrared imaging as well. So some of the properties are some examples that we have developed. I'm going to show you some examples in the upcoming slides. And the TEM image of how diamond-like carbon looks like is that you can notice that something like, there is this distance between the lattice points over here. So the D space corresponds to about 0.205. And then corresponds to cubic diamond, and you can see some sort of a crosshatch structure over here, and that signifies that it's kind of polycrystalline in nature, and these are all the amorphous regions of the entire film. And the hardness value when we experiment with what CMTI has developed is about, the mean hardness is close to about 32.7 GPa, and we have about coefficient of friction goes down to as low as 0.04 is the value for coefficient of friction. And this just to show how the coating looks like. So this is one layer, this is silicon wafer until here, and beyond this is diamond-like carbon. So these are the two layers of coating, and you can see how well this region is, and you will not find any sort of gap over here. It's atomically wrong. And then for transmission studies, if we coat diamond-like carbon on germanium wafer, which is typically used for night vision applications and night vision camera lenses, we can see that it goes close to about 93% is the change. So a bare germanium, if you notice, is about 47% is the transmission. When you coat it with diamond-like carbon, it can transmit up to 90% of germanium, and this is what we have done it on our. And also the sp3 hybridization is about 40 to 45% for DLC that we put on room temperature, which is quite a significant value. And we can see that it is pretty hard, and hence the hardness value is contributed to through this as well. So just to show how good our coating is, we have, this is about 30 angstroms, that's 3 nanometers. So at about close to 500 nanometers, or to be more precise, 485 nanometers. Our variation is just about 30 angstroms, or that is 3 nanometers. So it's as low as that, and that is even less than a percent, I can say. So for all safer sites, we say plus or minus less than 2% is the uniformity, but it's much better than that. So let me not worry about this and show you how the hydrophobicity that we have achieved. So we can play around with it. So if you want a wet surface that needs some sort of wetting, we can achieve that as if you want to have a hydrophobic surface. This is useful when you coat diamond-like carbon on the solar panel protection glasses. So what happens is that you have rain, you have sand, abrasive particles, and you want to clean it, self-clean it. So that way you have to form beads. So when there is a certain angle, if you are able to treat it with a very, very fine thickness of DLC, so there is some sort of a transmission available, as well as the water beads out, cleaning the surface. So that is where these sort of applications are useful. So these are peel-off tests, which is required for kind of, when you want to prove it on applications such as night vision, then you have to show that whether it peels off or not. So this is one of the work that a paper from Arade et al., which shows how it looks, how a germanium wafer on which diamond-like carbon is coated, and a microscopic image, when you peel it off, it becomes like this. But on our films, the peel-off did not occur, and we have also cleared the MIL standard test as per MIL C48497A. So we have already cleared all the tests, and it does not peel off. So it's as robust with respect to the addition is concerned. So some of the technologies that we have, it's readily available, and anybody can contact us. I think Shri Prakash Vinod, Center Head of SMDDC, and also the Nano Manufacturing Technology Center, when he was explaining today morning, he has already briefed and made my work quite light. But I just would like to tell you about how these coatings are. So this was made for demonstrating it to one of the leading watch manufacturers, and this was also for one of the leading knife companies in the country. And most of the surgical blades in the world are actually exported from India. So the manufacturer wanted to know if they can have for long duration surgeries, would DLC be advisable, so that the doctors don't have to change their surgical blades often. So for that purpose, we had done it. And this was for night vision camera lenses that we have done, coated germanium. Also, this was for one of the American customers. This, as I mentioned in 2 slides ago, that DLC had to be coated for both hydrophobicity and also for scratch resistance on solar panels. So this is what we have proposed as a solution, which is possible even on glass. And this is for low coefficient of friction, wherein for machine tool applications, you need guideways which do not have backlash and are extremely smooth. So these are the places where you can actually coat with DLC. And you can also coat it on plastic as an underlaying layer so that you don't have scratches on the plastic. So this was a research which, if I'm correct, I'm not too sure, but Nokia started it for their mobile case, mobile phone bodies long time ago, but I'm not too sure. Then even for cutting tools, you can use this. And just to show what difference that you can notice is that an uncoated cutting tool has a wear after about 35 minutes, you can notice a 26 micrometer wear. And a DLC coated tool, the wear is seen after 35 minutes is just about 10 micrometers. So we can say with confidence that DLC has absorbed most of the impact during the cutting, and hence it has subsided the wear of the cutting tool. And only after that, the coating has been removed, that you can actually notice that there is there is wear on the tool. So this is also very good for cutting tools. So I shall next be talking about carbon nanotubes in the next few minutes, and this is something which we develop at our lab. So what are carbon nanotubes? Just to introduce it to you, they are good conductors of electricity, and basically they are rolled graphene structures. And the new sort of allotrope of carbon, they offer ballistic conduction and offer good mechanical properties such as Young's modulus. So we have been working on super black coating. So this was for one of the top space research organizations of our country, with whom we worked and made super black coatings that goes into one of their satellites for imaging purposes. And also we have the CNT based UV sensor that we have developed for applications such as for engine combustion monitoring, wherein whatever whether to predict if the combustion is going on properly or not. So this is one of the applications that we have developed for. So it's just a sensor head. And then encapsulation of CNT using DLC. And this is basically for some sort of a thermal interface material that we have been trying around. And then we do have the TM of that and how it looks like, just to show that there is both, I can say the CNTs as well as the DLC which have been found. That is called. And this was my cover image of today's presentation, and this is titanium nitride. This we recently published. CNT is being encapsulated by titanium nitride for, again, thermal interface materials. So it looks beautiful, like, cauliflowers coming out. And then this is the TM image of how it looks like. So you can have a look at the coatings, both CNT and as well as the titanium nitride. So this is how the EDS image looks like, for carbon, titanium, and nickel. So I'm not going to go ahead further. So the next is the PVD coatings. This is my last two slides that I'm going to present. So what sort of PVD coatings that we are basically doing is that we have something like micro heaters, metrology artifacts, and this is flexible sensors that we are developing over at CMTI. And this is one crystalline ferrous oxide for an Italian customer that we have developed for certain applications. So this is how we have developed. This is how the film looks like. So this is what in brief I can say about our activities. So this is our lab, and this is the PE-CVD system, and this is the PVD system. So with that, I will stop sharing my screen. Thank you very much for your patient listening. And maybe if we have some questions, I would be ready to take.
Yeah, Manjunath here. Thank you for presenting. And before concluding, let me also check in the back end whether we have any questions. So as I can see, there are no questions on this topic. So we had only one question from Thadi Sivaprasad, that is on nano manufacturing technical session. Anyway, I'm going to forward the same to the concerned faculty.
Okay.
So there are no questions as of now in the Q&A. So once again, I'll just thank you and thank the participants also for joining for this session. With this, I will conclude this session. Thank you, sir, and let us move on to the next session. So
Thank you very much once again. I would like to thank CMTI and DSI for organizing this program. Thank you.
thank you. So let's move on to the next session on the topic microstereolithography, and the lecture will be delivered by our faculty Mr. Harikrishna Tota. So let me introduce our faculty. Mr. Harikrishna Satish Tota is a scientist at Central Manufacturing Technology Institute, Bengaluru. He received ME in Electrical Measurements and Instrumentation degree from the Department of Electrical Engineering, Jadavpur University, Kolkata in 2011, and BE in Electrical and Electronics Engineering from Andhra University in 2009. He joined CMTI in 2012 and involved in applied research and product development projects, TRLs ranging from 7 to 9. He involved in design and development of projection microstereolithography based systems, ultra-stiff ultra-precision turning machines and algorithms, and software development for ultra-precision measurement systems. He is currently working in the area of smart manufacturing, IIoT, Edge, AI, and Industry 4.0 implementations. So this is about our faculty, Mr. Harikrishna Satish Tota. So I'll be sending you his email ID for further correspondence through the chat box. So now over to you, sir.
Thank you, Mr. Manju. Is it audible? Is it audible?
Yeah, you are audible. You are audible, yes.
Yeah, I'm going to. Yeah, fine. I'm going to present the topic microstereolithography. Hope my screen is visible.
Yes, it's visible.
Yeah, thank you. Thank you, Mr. Manju, for introduction. So, I'm Harikrishna Satish Tota. I'll be presenting on microstereolithography. Focus and applications of microstereolithography. The content will be microengineering. I'll be discussing about microengineering, miniaturization, microfabrication processes, principles of microstereolithography, and classification of scanning.
Sorry for interruption. Hello, sorry for interruption. Yeah. I think the audio can be little. It can be clear.
Louder.
There is a slight breakage in the voice.
Yeah. Is it okay? Okay. I'll try to fix it up.
Yeah.
So is it okay now?
Yeah. Now it's fine.
Thank you.
Yeah.
So the microengineering. So basically, the microengineering deals with the design and production of small three-dimensional objects, usually to manufacture in high volumes at a low cost. So that is called as microengineering, and this definition is taken from the reference given here. So generally, we need things miniaturized versions, right, basically. So earlier we are using very big mobile phones, which has a limited features. Now we are using mobile phones very handy and which are having multiple features in the mobile phone itself. So the miniaturization is actually it's a key technology for making the devices smart as well as more efficient. So here I'm giving an example of one blood cell analysis machine here. So this uses a micro cell cartridge. So this is a tabletop equipment which can be miniaturized by using a microfluidic chip embedded in a device which can be connected to the mobile phone, and the diagnosis can be done with a drop of blood, and entire report can be seen in your mobile phone. So this has happened because of miniaturization of certain technologies. So not only in electrical and electronics engineering, but also in mechanical engineering and process of materials technology, basically. So these are the advantages of miniaturization, basically. Easy to handle, easy to mount, low cost, saving of material, saving of power. It will be fast and easy to integrate, saves space, and leads to volume production. So there are some disadvantages with miniaturization also. So the disadvantages are expertise is required. So suppose if you want to fabricate this kind of complex microfluidic chips or micro devices or lab on chip kind of things. So you need a lot of expertise, which expertise may be from different domains you may require. So the fabrication is complex. You need very complex fabrication technologies to make these things possible. So it could be use and throw kind of devices. This may cause environmental hazards, but this is one disadvantage with miniaturization because of low cost, and the maintenance is not possible in some of the miniaturized devices. These are all meant for use and throw kind of thing. You cannot do maintenance, so it needs a suitable packaging. Suppose if you a lab on chip kind of device, you need to package it properly. So the package is very critical and very complex. So before going to the micro steel, to use the length as 1 unit, just for an idea. So here, I know everybody knows unit of length meter. Imagine the length of micrometer. It's very hard. So even we'll be discussing today on nanometers. So if you see, for example, if you take a human hair, the hair will be around 60 to 100 micrometers of thickness. I mean, hair dia is around 60 to 100 micrometers. So in that way, you can imagine 1 micron how small it would be, and 1 nanometer how further small it would be. So coming to the microfabrication, in scientific and technical committee of physical and chemical machining process of set, it is defined as 1 to 500 micron. The range of fabrication is called microfabrication. That means if you are fabricating some kind of macro device which is having a micro feature which are ranging from 1 to 500 micron, so that would be called as microfabrication. Or you can fabricate micro devices or micro components 1 to 500 micron range, that also called as micro fabrication. That is the range is given by the SIP. So the microfabrication is the foundation technology to realize miniaturization. So coming to the today's topic, microstereography. The meaning of microstereography is micro means very small, but for the SIP it is ranging from the fabrication, which is ranging from 1 to 500 micron, is given as microfabrication. So the stereolithography, in the sense, stereo means 3D. So lithography means writing. So the process uses a laser beam or a pattern UV light to create a 3D micro components. So that is the reason it's called as micro stereolithography. So there are 2 different types basically: the scanning type MSL process and the dynamic mask type MSL process. In scanning type, basically the laser scans point by point, and it solidifies the photocurable resin, so that you will be able to fabricate micro component. So in dynamic mask method, what would happen is it's completely different. So here the entire layer, the layer is projected with the UV light or pattern UV light. So entire layer will be cubed at one shot curing. So that is the difference between scanning method and dynamic mask method. So there are 2 types of scanning methods or scanning processes. One is basically it is called as integrated hardened polymer process, that is IH process, that is scanning MSL. So another one is super IH process, that is 2-photon microstereolithography, that is 2-photon MSL. So coming to the projection microstereolithography, this is called as projection method, and it is called mass IH process, mass integrated hardened polymer process. So basically the scanning MSL, if you see, the scanning takes place layer by layer, or actually it is point by point scans, and it completes layer by layer. The focal point of the laser remains the same. The layers are integrated. So this is the typical overview of in-house developed setup in CMTI in early 2010. This uses a laser basically. This is a laser. So this laser dia will be around 3 mm dia. So the 3 mm dia of laser is passed through AOA. the acoustic optic modulator. So the acoustic optic modulator, it diffracts the laser into four orders. The second order diffraction is captured on the reflecting mirror. So that will be passed through the conditioning, the beam conditioning optics, so called beam expander, and certain set of apertures and lenses. So that at the end of the projection, you will get 50 to 50 micron to 100 micron. Maybe you can further scale it down to 30 micron, 20 to 30 micron dia of the laser. So that laser will be scanning a photo curable resin. So this is a basic overview of scanning MSL based technique. Scanning MSL based technique uses a CAD model basically. The CAD model, which is developed in CAD modeling software, that will be sliced into layers. Basically, the layers will be used for part generation. The part generation after that will be post curing, and then we will be giving it for user interface. So this entire setup was built at CMTI, which is based on LabVIEW based control setup. And at the end here, you can see one XYZ stage. So this is the XYZ stage, which having a cantilever arrangement, which is a sample holder. So that will be dipped in a photocurable resin. So the photocurable resin initial layer will be set up on the beam will pass through the laser, AOF, and set of beam conditioning optics, and then at the end you will get a 30 to 50 micron range of laser beam that will be scanning based on your laser part generation by control software. So that's how it scans point by point, and it builds the micro components. So another setup what we made for academic use or kind of experimental use, which is a low cost setup. It's called compact microscopy. So here, instead of laser, we use a UV source, UV LED basically. So UV LED will be conditioned using conditioning of optical conditioning system. So at the end, you may get 50 to 100 micron range of beam. So that beam will be scanning on the sample. So here the resin is kept in a vat. So the program will be loaded to PC, control PC, and which will be passed to the control commands to the stage as well as the laser. So the stage will be moving in XYZ directions, and simultaneously the laser will be focusing on the photocurable resin. So the basic process is called photopolymerization. That's what happens to get the part fabricated. Photopolymerization, basically, it's a chemical reaction process which happens when the photocurable resin interacts with the laser beam. Here, the basic chemical used is HTDA, hexanediol dichloride, which is mixed up with the photo initiator that will be used as a catalyst for the chemical reaction, the benzyl ethyl ether. So that will be mixed, and then that will become photo. The photosensitive resin, when it interacts with the laser beam of a particular wavelength, so the photo initiator absorbs the UV wave, and then it starts forming free radicals. Free radicals interact with the actual HDA molecules and forms chain reaction. So entire process is called photopolymerization process. Once the photopolymerization starts, so it will be linking all the particles and will find the photopolymer. So we find the liquid photopolymer, hardened photopolymer. So that's how entire process happens, and finally you will get micro components. So here, certain process parameters are there. You can optimize depending on your requirement. So this is one example. The process parameters are basically the laser spot size and laser energy and scanning speed. These are the three process parameters which can be varied to get different resolutions, different accuracies. Here, one example is given here. So the 50 micron beam, the laser beam, if you scan, the scanning that will very coarse. It's shown here on the left side. So the same way, if you beam dia to 10 micron range, and if you scan, that will be very final. So there is a trade-off between reducing the beam dia. So if you are reducing further, you need to pump more energy to get the polymer solidified. So that's why we have to limit the beam dia shaping up to 30 micron, max to 20 micron range. So here, by conditioning the beam, when you're projecting on your uh, photocurable polymer, you can able to get a 3 micron resolution, maybe 1 micron resolution also. So this is one patented process, the CMTI. You can see here the fabrication of microneedles. So the fabrication, this microneedles fabricated using this technique. The base dia is about 50 micron, and the IP is about 30 micron. So this using a 20 micron beam dia, and you are able to get a 3 micron tip. So that is the key technology and process technology what we developed. So this has various applications. This microneedle arrays has various applications. I'll be discussing in the application section. So these are the two platforms, scanning based techniques. Techniques in sense, one is for R&D use, and another one is for academic use, which is low cost one. The two platforms which we developed in 2013 and 14 simultaneously, subsequently. So another coming to the another process called super IH process, which is very advanced process basically. Super IH process is also called as two-photon polymerization. So here, the two-photon polymerization happens because of femtosecond laser interactions. So here, if you go to the atomic structure, there will be
Sorry
orbits.
to interrupt.
Electrons will be spreading in orbits, right? So when you
Hello.
give some energy to the outermost electron, so that will jump next outermost orbit.
Hello.
So that's what happens. Actually, here localized photopolymerization happens with the two photon interactions. So how it happens is, so here the X0 object, it will be, suppose if we
Hello.
let's assume one electron is orbiting in S0 orbit. So if you give one drop of energy, use normal light or laser, it jumps to next orbit. So this
Hello.
time is called state transition time. In this time, if you shoot another pulse of laser, so this will jump to the next outermost orbit. So that is the reason here, instead of one photon interaction, here two photon interaction will happen, so that it jumps to next outermost orbit. So this causes very localized photo in nanometer. So that's why it is confined to nanofabrication, not microfabrication. So this happens inside the resin, not on the almost surface of the resin. It happens inside. So how it happens? Two phone process uses a chemical laser, which is having data can be 800 nanometers. Pulses will variable focal length objective lens, by using which it can detect inside the resin basically. So this is what I'm showing it here. So which
Hello.
scan scanning it inside the resin. So this is how the components are built using two photon polymerization technique.
Hello. Hello. Sir, your voice is not audible. Hello. Hello.
Is it audible? Anybody? There is a technical issue.
Yeah,
Is it
that's what
audible?
you. Now it is audible. There was a. It was absolutely silent
Uh,
actually. Now your audio is clear. Now again it's breaking. Okay. Shall we conclude the session?
Okay, going ahead. Hope things are fine. So coming to the mass IH process, it's also called production microscopy. So it is the mass IH process, which is in-house called the CMTI. Here you can see the entire setup, which uses a UV LED and a collimator rod lens, and that UV LED will be focused on digital micromirror device, which generates the patterns. So micro patterns will be projected onto the photocurable resin, so that the photo fabrication, photopolymerization happens, and micro components will be obtained using this process. So this is the in-house build setup. Here you can see this is the actual setup, which is which used for fabrication in this enclosure. So this here, which uses a uh, photocurable resin which is kept in a vat. Uh, so this is the micro positioning stage, and this is the DMD chip. So the DMD chip projects the micro patterns, and the micro patterns will be projected onto on a UV resin, so that it starts shooting. I'll show you one video here. You can see here this connected truss micro glass structure, which model and will be sliced into images. So these sliced images will be fed to digital micrometers. So generate the patterns according to the sliced images, and which will be projected onto the photocurable resin. So this is the photocurable resin on a back, and which will be cured. So this is how after truss structure, lattice structure is fabricated using this. Uh, so this is what exactly happens in projection methodology technique. So we use a CAD model to fabricate let's take example of structure here. Uh, Structure, which will be sliced into images after converting into STL format. Then the slices will be put to the DAB chip process basically, and we'll be setting up process. So we will fabricate components, which will be cleaned and will be post processed and post cured, so that after curing we get an actual component which you design in micro 3D form. So this is the entire process. So this, which we have fabricated for that purpose. So the micro turbines, micro gears, springs, you can see some other sensor components. So you can see the SCM uses of the micro components, micro needles, and stints. Some of the stints and micro lens arrays. Here you can see the surface finish of the cube part, cube in nanometers basically. Few tens of nanometers surface finish directly will get the fabricated component once you do the excessive resin from the cube components. So you can see we have also tried the micro needle here. There will be no stepping effect. You will get a smooth curvature over the micro components. There will be no stepping effect here. So we are able to achieve the tip of the microneedle about here in this image it is about 11 micron. There is possible to achieve up to 5 micron. So that is the capability of the equipment what we have in house. So these are the some of the biomedical components which we tried the trial purpose using our in-house built equipment. The trial looked at microneedles, hollow microneedles for a drug delivery purpose, cardiovascular stents, biomedical scaffolds, and modified heart valves and with a cup support. These kind of biomedical resins also we can use. We can fabricate and use it for experimental purpose, uh, for experimental studies and even for real time use. So these are all fabricated using biocompatible and biodegradables. So coming to the applications, the microcirculatory applications are widespread into various industries: biomedical industry, jewelry industry, and manufacturing industries, MIMS and sensor fabrication processes. We can use this kind of technique. Coming to one application, the microneedles. So the microneedles can be used as a microneedle arrays for biopotential electrodes. So the electrodes consisting of microneedles will be penetrated to the skin, which is a non-invasive. You will not feel any pain. It is a painless process. The advantage of using microneedles is you can acquire better signal than the conventional techniques. So this is the project what we have done earlier for one of defense statistics at lab. So coming to the biomedical components, the coronary stents basically. Metal stents have some disadvantages. They will be there for lifelong, and the clogging happens once again even after installation of stents. To avoid that, now people are going for novel polymeric stents, so that biocompatible and biodegradable polymeric stents, so that they do their job and they disappear. There will be no further clogging of arteries even after installation of the stents. This is the ongoing research is happening. So for that purpose, we have already made stents with the biocompatible and biodegradable. You can see here cardiovascular stents, which is used. The material used is biocompatible and biodegradable. This is the technology we have along with the equipment. Coming to the micro springs, the micro springs used in energy harvesting devices. So the magnet will be placed on the polymer strings. So this magnet will be vibrated in a coil setup, so that you will be able to harvest the energy based on Faraday's. Coming to the scaffolds, biomedical scaffolds, you can use it for dentistry, you can use it for tissue engineering, you can use it for application of soft biocompatible implants. So these are the applications, biomedical applications of microcirculatory. So micro pumps and micro mixers for MIMS. This is in-house R&D we have done. So this is for micro mixing, efficient mixing of two different liquids using a microfluidic channels. Medical applications, as I explained already, one is for biopotential electrodes, another one is for drug delivery, painless drug delivery. We have supplied one of our customers for the same application. Even for vaccine, mass vaccination purpose, painless vaccination purpose, you have concentrated properties applied on microneedles, biodegradable microneedles. The patch is placed on the skin and it pressed against, so that the needles penetrates and release the drug painlessly. That is the concept. So coming to the microneedle scaffolds, 2D and 3D scaffolds, tissue engineering applications you can use it. So mechanical micro gauge, we already shown. So this is the confocal images of the micro gauge we fabricate using MEMS applications, micro gears, components, and MEMS cantilevers. You can fabricate micro cantilevers, and for biodetection, you can put some antigen on that, and you can use it for bioscience applications. You can validate your design. Suppose if you have the requirement of micro design, micro machine application, or micro engineering applications. So if you want to quickly validate your design, you can use this one and you can validate your designs. So you can also do a fabrication also. by mixing resin with proportional quantity of nano powders, alumina or zirconia powders, and you can cure it and you can get the ceramic micro parts. So it will be a ratio mixed. Actually, it will be 25% of resin and 75% powder. So that will be defined depending on your requirement, and you can fabricate ceramic components. So once you sinter it or debind it at 800 degrees, you get a green part. So the green part further sintered at 1600 or 1800 degree centigrade to get actual ceramic component. There will be a shrinkage of around 20 to 25% is expected. So if you want some 1 mm dia, you need to design it for 1.3 mm, 1.2 mm design, and then you fabricate and you get 1.3. Once you center it, you get actual dimension what you require 1 mm. So after shrinkage, so that's how you need to optimize the design to get and we are working on the different that's about Microscope. Is involves. I can take up now. Manjunath,
Yeah. So let me just confirm you, sir, whether we have any questions from the participants. No, there are no questions in the Q&A platform. So thank you for delivering the lecture. Participants, you can write to us anytime again on this topic. We will come back to you. So thank you for delivering lectures. Now moving on to the next session. It is on laser micro machining, and this lecture will be delivered by Mr. Sunil Magadam. So this is about our faculty. Mr. Sunil Magadam is a scientist at Central Manufacturing Technology Institute, Bengaluru. He has done his post-graduation ME Mechanical in Manufacturing Science and Engineering from UVCE, Bengaluru. He has over 8 years of experience in the field of precision engineering and advanced manufacturing. His areas of interest are laser-based micromachining, surface micro-texturing, cryogenic machining, development of biomedical devices, microfluid devices, and indigenous metrology artifacts. He has published over 10 publications in national and international journals and conferences. So email ID of Mr. Sunil Magadam I'll be sending you through chat box. So now over to you, sir.
Yeah, thank you, Manju, for the introduction.
Yeah.
I am sharing my screen. Is it visible to you, Manju?
Yeah, it is visible.
Yeah, good afternoon, everyone. Today I am going to give a presentation on laser micromachining. Myself, Sunil Magadam, scientist at CMTI. So basically, in this presentation, I'm going to cover about the work what we have done in laser micromachining activities at CMTI. Basically, we have two laser systems with us at CMTI, femtosecond laser and excimer laser. I will brief you about the work what we have done by using these two lasers. So why we use laser for material processing? Because it's a not all of you know that it is a non-contact method, unlike conventional machining process, and no solvents or chemicals are used during machining. It is a very clean process, very environmentally process, and selective material removal is possible in laser processing. That means you can accurately remove a surface material without affecting the material beneath. And we can machine a wide range of materials like fragile, ultra thin, heat sensitive, and highly reflective surfaces by using laser machining. So laser classifications, going through the classifications, based on their source of emission, lasers are classified as a solid state laser like Nd:YAG lasers, titanium sapphire lasers, then semiconductor lasers like DPSS, it is diode pumped solid state lasers, then liquid crystal lasers like dye lasers. Basically, these are used to study the emission and the absorption spectra of various materials. And another section is a gas lasers like argon fluoride, krypton chloride, krypton fluoride, etc. And based on the second classification is based on the nature of emission, like a continuous wave lasers, like a CO2 lasers, and discontinuous, that is a pulsed lasers. They are femtosecond, excimer, etc. In CMTI, we have these two pulsed lasers, femto as well as excimer lasers. And laser micromachining, coming to laser micromachining, first it was demonstrated in 1980s. Heat diffusion into the material is a major problem in laser machining. So in early 90s, University of Michigan scientists has discovered that the heat transfer from the laser beam to workpiece could be defeated if we use ultra-fast lasers. That means heat diffusion takes place in picoseconds. If we use a laser which is having a pulse width of lesser than this picoseconds, then we can easily beat the heat propagation to the material. So there comes a pulse lasers. So ultra short pulse laser, that means pulse duration is less than 10 picoseconds. They're called ultra short pulse lasers. They're also called ultra fast pulse lasers. Then long pulse lasers, like if the duration is longer than 10 picoseconds, they're called long pulse lasers, where the heat, their pulse width is longer than the heat diffusion time. So you all know that heat diffusion into the material is undesirable in micromachining. So what are the adverse effects of long pulse lasers? See, you are seeing this picture at the left side. So during this micromachining using long pulse lasers, it contaminates the surrounding, and it melts and removes the material larger than the spot size. Because of that, a very fine machining is not possible by using long pulse lasers. And also damage to adjacent structure due to heat affected zone. So heat propagates through this heat affected zone, can cause mechanical stress and create micro cracks. So during use of this component, these micro cracks can propagate and causes premature failure. So we have to avoid heat affected zone during machining. So then it also forms a recast layer, which is a resolidified layer whose properties, physical and chemical properties, are very different from the unmelt material. And this is a very weak, mechanically weaker section. We need to remove this recast layer. And even if the spot size is 1 micron, the minimum feature size what you can get in long pulse laser is not less than 10 microns. Like for example, in CO2 lasers. Then machining with ultra fast lasers, you can see here the duration of the laser pulse is shorter than heat diffusion at time. That means there is no heat propagation into the material. Because of that, there is no melt zone, no micro cracks, and there is no recast layer, as well as a heat affected zone is very minimal by using ultra fast lasers like a femtosecond lasers. See here you can see the clear difference. So what are the main advantages of ultra short pulse lasers like femtosecond lasers? So there is no thermal damage. There is no thermal damage like long pulse laser, and machining quality is very high. You are going to get a very high machining quality, and heat sensitive materials can be machined by using ultra pulse lasers, and you will get very unmatched accuracy. And here the right side image clearly shows that. So with the nanosecond, here you are going to get a debris kind of thing, that is a recast layer, and the machining quality is also not that clean. Whereas with the femtosecond laser, you can see the machining quality. It is a very clean, and you are going to get a very accurate quality. Then coming to laser micromachining method, direct writing and a mask projection system. Yeah, direct writing is by using directly the laser, you are going to machine or process the substrate, like a desired pattern fabricated by translating either a sample or the substrate, like in femtosecond laser. Whereas a mask projection system, you are going to use a mask between a laser beam and the substrate. So the whatever feature you want to create it on the substrate, you need to have it on the mask. That means a given feature on the mask is illuminated, which is projected on the substrate, like in excimer lasers. So the femtosecond laser system, what we have at CMTI, so which is a Clark MXR make, and which is having a wavelength of 75 nanometers and a stage resolution of around 1 nanometer, and it is having a laser output power of 1 watt and repetition rate of 1 hertz to 2 kilohertz. It is having a pulse width of 10 picosecond to 150 femtosecond, and the traverse is around 150 by 150 by 100. And a minimum feature what we can machine with this system is around 1 micron. So coming to the application of femtosecond lasers. So micro holes. So you can see the image here, micro drilled holes on coated carbide cutting tool insert. So you are seeing a 10 by 3 array of drilled holes, which are having a size of 10, which are having a diameter of 10 micron with a depth of 10 micron. So this is mainly used to improve the cooling effect during machining. So this is one of the application. So next is microneedles. So as our colleague Mr. Hari Totta has previously explained regarding the microneedles, these microneedles are used in drug delivery, that is in biomedical application for drug delivery and other applications. So you can see the 4 by 3 array of microneedles, which are a square needles of 150 by 150 cross section and a height of 700 micrometer. Whereas right side, you are seeing a circular microneedles with the outer dia of 100 micron and internal hole of around 60 micron, whereas the height is around 300 micrometers. They are done in femtosecond laser on SS304L material. And next, master mask for sputter coating. So in PVD coating, that is a sputter coating, you need a mask in order to create any designs on a substrate in a thin metal coating. So you can create this kind of mask in femtosecond, because you all know that if the thickness of this mask increases, then you are not going to get a very straight edge during the coating. So here the thickness what we have used here, a stainless steel sheet of 50 micron thickness. This kind of very thin sheets, the machining is not possible in any conventional processes. So the most appropriate process is laser machining, whereas a femtosecond system. Here the feature size is around 100 micrometer. And again, this is one more example of master mask created in stainless steel sheet of thickness 200 micrometer. And micro heaters. So these are done. These are processed in femtosecond laser on a nickel sheet of thickness 20 microns, a very thin sheet. Here the rib width is around 100 micrometers. And these micro heaters are used in some strategic applications. Next, micro cantilever. So here you can see the micro cantilevers processed using femtosecond laser in copper material, that is a sheet having a thickness of 5 microns. So it is a very thin sheet. So you can see the quality of cut. So it is very clean cut. And this kind of machining is not at all possible in conventional process. And next, micro grippers. You can see the micro grippers created in a smart material like a nitinol, and where the gripper arm size is around 30 by 100 micrometer. Then microfluidic channels. Here the microfluidic channels of cross section 70 by 70 micrometer, whereas the 50 by 50 micrometers on borosilicate glass. So this kind of microfluidic channels are used in biomedical applications, usually for single cell analysis and blood analysis, etc. And in another application example, where the this is right side is showing a confocal image of an array of 25 by 10 of micro holes with a dia of 10 micron and a depth of 5 micron. This kind of microfluidic channels in glass substrates can be easily fabricated in a femtosecond laser. And another most important application, that is subsurface machining using femtosecond laser. See, you are seeing the channels here, the straight channels. These are inside the material. So they will connect over here. And here also you are seeing this channel. It is a transfer material. It is in borosilicate glass. These are underneath the material. So this is one of the very good application in MEMS applications. Very good application. Here you can create a channels inside the glass or inside the material. That is a transparent material. Next, micro slot cutting, or you can say it as a dicing. This is again a glass material. We have created a micro slots. So this kind of wafers are used in MEMS applications. Next, another application. This is an internal R&D at CMTI. We have synthesized the nanoparticles, basically copper nanoparticles of average size of 40 nanometer in colloidal form by using the femtosecond laser. So if you consider nanoparticle synthesis by chemical route, so which are not desirable in medical applications. So one of the alternative method is to get pure nanoparticles by using a femtosecond laser ablation. So coming to the applications of copper nanoparticles, copper and copper oxide nanoparticles. So like a biomedical, industrial, environmental, and agriculture applications. Can see the biomedical application. They are used in wound healing, antibacterial, antifungal, anti-cancer, and etc. applications. Whereas in industrial applications, electronics, superconductor applications, sensing, and etc. Whereas in environmental applications, they are used in solar energy transformation, nanometal lubricant additives, etc. Whereas in agriculture applications, they are used in a nanosensor to detect fungus infestations, food industry, and they are used in plant growth, etc. They are having a very good applications. And one of the alternate method to produce these kind of pure nanoparticles is a femtosecond laser ablation. And another developmental work is carried out at CMTI is the development of metrology artifacts. These artifacts are basically used to calibrate precise instruments with non-contact method of measurements like high resolution optical microscopes, video microscopes, profile projectors, etc. So basically these artifacts, the instrument manufacturer as well as users are importing such kind of artifacts. So we thought to develop indigenous artifacts. So we have used a femtosecond laser to create this linear standard glass scales as well as angular standard glass scales. They are nothing but gratings we have created by using a femtosecond laser. So this technology is already being disseminated to the one of the industry. And another application of femtosecond laser is a diamond marking. So we have masked this portion as a part of our NDA to avoid complications. So see, you can see a diamond marking is done by using a femtosecond laser. Very good quality marking can be done. So basically, a femtosecond laser can machine any material, polymer, glass, metal, non-metal, even a diamond also it can machine. And another application for biomedical applications, that is microhole drilling of vials and ampoules. This is required for CCIT testing. There is a container closure integrity testing that we have successfully established at the CMTI. Then after femtosecond laser system, we have another system called excimer laser system. Basically, this is a UV laser system, which is of optic make, and here the beam delivery is of coherent lasers. The wavelength of this laser is we have two options in this: 192 as well as 248 nanometer. That is argon fluoride and krypton fluoride. Here the pulse energy, average pulse energy is around 400 millijoules for krypton fluoride and around 200 millijoules for argon fluoride. And here the pulse duration is in nanoseconds, that is in 20 nanosecond. And repetition rate, that is a maximum repetition rate is around 50 hertz. and whereas the beam size here is 24 by 10 mm. It is a rectangular size. Minimum feature size what we can machine with this system is around 1.5 to 5 micron. And here we use a mask between the beam and the substrate. And here the traverse, the maximum size of the material what we can handle is 200 by 200 by 50 mm. Some of the applications of hexamer laser system, that is in biofilters, ceramics, then collectors channels of around 100 micrometer feature size, then micro lens, that is a fiber coupling lenses, wire stripping, and even we can fabricate polymer stands by using hexamer lasers. And the work what we have carried out at CMTI by using hexamer laser is, so we have fabricated micro lens array of 5 by 5 of size. Diameter of the lens is around 900 micron, and with the center distance of 1 mm in x as well as y direction, and we have a lens sag of around 70 micrometer. This kind of lenses are used in fiber coupling, imaging systems, sensors, illumination systems, etc. And another application is a micro heater. Here, so this is a glass which is coated with a nickel with some few nanometers. We have just etched this nickel coating without affecting the base substrate. That means based on the design of the micro heater, we have just etched out the nickel coating from the glass. So the minimum feature size is here is around 100 micrometer. Another application is microscopic calibration mask. These are used to calibrate again the microscopy equipments. These are also import substitutes. We have fabricated in hexamer laser. These are chrome coated glass. We have created small features ranging from 1 micron to 1.5 micron to around in mm range. Here also you can see various features we have created in a chrome coated soda lime glass. And another application is a thin metal coat etching. It is like a previous application itself. Then etching of chrome coated glass for this is used in the EMI application. So one of the application that is a important application in hexamer laser is you can remove any thin metal coating without affecting the base material. That is a selective material etching can do. That's all from my side. If you have any queries, you can contact through a mail ID. Thank you.
Yeah, thank you. So let me check whether we have any queries.
Yeah, please, Manju.
No, as I see, there are no there are no queries in Q&A. So thank you for delivering your lecture. So thank you, participants. Please come back to us on this. So shall we conclude? And what time shall we have the session on sensor technology?
Around 2:30.
Hello?
We have around 2:30. Manju.
2:30, is it? Okay. Okay, thank you all. And till so now it is 2:23. So all of you please come online by 2:30, and the session will start on the topic sensor technology, and the coordinator Mr. Pradyumna will take over. Okay, thank you.